Good. Okay, I'll stick you down there.
Mplus worked.
What?
The remote login, it worked.
It worked. Okay, excellent. Good to hear it. Okay, so there we go. So we have an ambitious agenda today because normally on week 2 I would have shown you how to do path analysis in Mplus, and on week 3 I'd show you how to do CFA in Mplus. But today I want to show you how to do both path analysis and CFA. Although once you get going in Mplus, I mean, you'll see it sort of generalizes, right? So I think it'll go faster doing both of those. And then we do need to finish up talking about CFA. And then I also, what I skipped last week from path analysis that I would normally do on week 2 is talking about how to fit path models, like the model sort of fitting or model building steps, which I think it makes much more sense to go through in Mplus. So those are our plans for today. So we're going to be talking about fitting path models. We're going to be finishing up CFA and talking about how to fit CFA models. And we'll also be talking about how to use Mplus, which, I mean, sometimes people are really scared about Mplus before they use it, but you will see it is a super, super easy to use program. I mean, like any program, you kind of have to get to know it a little bit, but it is actually quite easy to use. And once people sort of get started with it, they tend to like it very much. Okay, so that's the plan for today. So the first thing I want to talk about is sort of how should we think about the process of fitting path models. And so let's take a look at this path model for a second, the one that's on the board, on the smart board, and tell me where do you notice that there are over-identifying restrictions, which really means where are there not linkages, right? Where are there omitted or deleted paths in this model? So if it were a just identified model, we'd have a linkage between each and every pair of variables. But we don't have linkages between every pair of variables here. So where do we not have those linkages? Yeah.
From ASP, a direct effect from AST to HMK and GD to HMK?
Yes, that's right. And I should probably tell you what those things stand for too, so they don't just seem like random letters, but that's right. So ASP is academic self-perceptions, GV is goal evaluation, SR is basically motivation. It's motivation, self-regulation, but let's just call it motivation for short. HMK is homework, and GPA, that one's kind of obvious, right? It's your GPA. So basically what this model is saying is that like academic self-concept, right, or academic self-perceptions and how much you value the goals of school, that valuing the goals of school and feeling good about your academics, those both predict the level of motivation that you have. And then motivation predicts homework completion. And notice there, again, you were right when you said there are no direct linkages from ASP and GV to homework. So what that means, what this model is really saying is, okay, motivation, how motivated you are, predicts how much homework you're going to do, right? That makes sense. And this is saying, you know what, your academic self-perceptions don't actually predict homework completion behavior after controlling for motivation. So like, the better you think you are academically, the more motivated you're going to be for the subject, and the more motivated you are for the subject, the more homework you're going to complete. But once I control for motivation, I don't think there's going to be like an independent contribution of academic self-perceptions on homework completion. That's what this lack of direct path is really saying to us. And the same goes for goal valuation. You were right. There's no direct path from goal valuation to homework completion behavior. And so that's saying like, yeah, valuing of the goals of school makes, or valuing the goals of school makes me more motivated, right? Being more motivated makes me complete more homework. But like after controlling for motivation, valuing the goals of school doesn't necessarily directly contribute to increased homework completion. Make sense? Okay, great. And then there's actually another linkage that isn't in this model. Where, yeah?
Direct path from motivation to GPA.
That's right, the direct path from motivation to GPA. There is no direct path from motivation to GPA. So again, here we're saying, okay, being more motivated means that you complete more homework. Completing your more homework results in a better GPA. But after controlling for how much homework you do, motivation in and of itself doesn't have any direct effect on your GPA, right? Academic self-perceptions and goal valuation, however, do. So here, this part of the model, we're saying, okay, your GPA is predicted by your academic self-concept, how much you value the goals of school, and how much homework you complete. But after controlling for those three things, motivation doesn't have like is not going to make an independent contribution or have a direct effect on your actual GPA. Does that make sense? So conceptually, that's what this model is saying. And we've noticed now there are actually three, I'm going to call these conceptually omitted or deleted paths. I used to always call them deleted paths, which may be confusing. And as always, I don't know if it's confusing or not. I mean, they are deleted. But anyway, as I was writing the book that you all have those three chapters from, I ended up changing that phrasing to conceptually omitted paths. So I've tried to put in the PowerPoints conceptually omitted and then in parentheses deleted, because I know I'm going to slip sometimes and say deleted paths when so just know conceptually omitted paths and deleted paths are the same thing in this case. And what we're really talking about here are, where are we not putting a direct path, which again translates into saying that after controlling for those other variables that are actually directly influencing GPA, let's stay with GPA for a second. If we don't have a direct path from motivation self-regulation to GPA, I'm really saying that there is no direct effect. So I'm saying that path, I believe, is 0, which doesn't mean that I'm saying that motivation is uncorrelated with GPA. It means that I think that any correlation between motivation and GPA is actually going through, right, is being mediated by, so it's like a little mediation model, if you're familiar with mediation. Any effect of motivation on GPA is being mediated by homework. So this doesn't mean there isn't a correlation, right? Because we've done those model implied correlations now, and we've also done things with direct, indirect, and total effects. It doesn't mean there isn't a correlation between those two things, and it doesn't mean that there isn't an effect of motivation on GPA. It just means that effect is mediated by homework. Does that make sense? So you could imagine, I mean, again, this is like my toy model. We're going to use these data for, I think, the first 3 examples. So right now we're doing like a path analysis that our CFA example is going to use the same set of variables. Actually, I think we're just going to look at academic self-perceptions, goal evaluation, and motivation self-regulation. We're going to make those latent constructs instead of observed with indicators. And then I think next week we'll actually do something where we put all that together and look at a hybrid model. So we're going to use the same example with this toy data for 3 weeks. I mean, I think, again, conceptually makes sense, right? I mean, you could maybe disagree with it, but let's go with it because it's the example we use for class. As long as you kind of get the gist of the model, I think that's the most important thing. Okay, so we have these 3 conceptually omitted paths. Who decided that? The researcher, right? You decided that if this were your model. But here's the thing. Maybe you're wrong, right? Maybe this model is wrong. Maybe actually you shouldn't have omitted that path. Maybe by omitting one of those paths, you have sort of an omitted variable problem where there actually is a direct effect of goal evaluation on homework, or there is a direct effect of motivation self-regulation on GPA. And if you only fit this model, and this, like, if you just fit this model and you say, here's my model, this is what I think, this is how it fits, you don't necessarily know if you're wrong, right? So it's a really good idea. And here's, well, actually, I think I'll go to my next slide. Okay, I'm going to say, I think, and I hope this is changing now, but the sort of the traditional approach to fitting structural models in SEM, not by everybody, but by sort of by some is to just estimate that specified model. So just take that conceptual model, run it. Look at the fit of the model. Does it have good fit? Great, it has good fit. I'm going to go out and publish this, and I'm going to say, this is my model. It fits well. What does it mean to fit well? Well, we're going to talk about that next week. And there's some controversy about like how good is good for fit, but you know, if I feel like the fit is good enough, I'm going to just go with the model I have. I'm going to say this is good enough fit. I'm going to write up the article. I'm going to sell everybody on my good fitting model. And let's say it doesn't fit well, then I'm going to be like, oh, I don't know. Let me just start adding paths, see what I can do to make this model fit better, right? In sort of a ad hoc, post hoc, arbitrary way. Okay, don't do that. That is a bad idea. I'm going to give you a much more systematic way to think about this model building and testing that I think is much more defensible. Oh, not now. I do need to talk to them because I had to cancel my appointment, but all right. So don't do that. This is what we're going to do instead. I'm going to give you a sort of a 3 steps. Two are for sure. The third one is optional, actually. So I'm going to give you some steps in terms of building and testing these models. So step 1 is the test of conceptually omitted or deleted paths. And what that means is I'm actually going to fit the just identified model. And to do that, I'm going to have to know what I'm going to have to be able to take the conceptual model and turn it into a just identified model. So what's a just identified model again?
To have no degree of freedom.
Yeah, a just identified model has 0 degrees of freedom, and that means it has one linkage. Yeah, it has, you're right, paths between every set of 2 variables is going to have a linkage. There's going to be a path or a correlation. There's going to be some linkage between each, every pair of conceptual variables. Notice I'm saying conceptual variables here. So I'm not talking disturbances, okay, or measurement error. I mean, we're not even talking about measurement error here because it's a path model, but we're talking about the actual variables of interest, which in this case, because it's a path model, are all observed variables. So going back to my, let me go back. Going back to this example, we've already identified that there are 3 conceptually omitted paths. So academic self-perceptions and goal evaluation to homework, motivation self-regulation to GPA. So those are my 3 conceptually omitted paths. So my first model is not going to be this model. It's actually going to be the just identified model. This model that adds those conceptually omitted paths. So we're going to fit the just identified model. Okay? And why are we going to do that? Well, and this is why it's, this is sort of the logic. We're going to fit the just identified model with an interest in looking at those conceptually omitted paths. And then in this first run, we're actually only going to look at the paths we thought we didn't need. Which is like, okay, so after control, which if you think about it, the logic kind of makes sense. After controlling for all of the pathways I think I need that are conceptually important, do I really not need these paths that I think I don't need? That's the logic. Like, I think I don't need them. But before I say these paths are unnecessary, maybe I should check that I really don't need them. Yeah.
So actually, like, prior to step 1 is to make the model with the conceptual omissions, right? Like, you wouldn't just start just identify and then, like, in order to look at the 3 paths that you're.
No, I'm going to start with just identify. I am absolutely not going to start.
Like, which 3 paths you, like, as you just said, you'll be looking at the 3 paths you thought you didn't need.
Okay, well, so let me say this. Like, on paper, I might start with the conceptual model
right?
and then figure out what my deleted paths are. But in terms of like actually running the model, yeah. So I follow you. Yes. The first step is have a model, right? Have a model. You have your conceptual model. I mean, kind of assuming that before you come, you've got the conceptual model. But you're right. First step is figure out your conceptual model, right? Second step is figure out what's deleted or omitted conceptually from that conceptual model. But now that I'm going to go to Mplus or I'm going to go to my SEM program, step one in running models is going to be take that conceptual model, figure out where the deleted paths are, and instead of starting with your conceptual model, which is oh so like tempting, right? Because that's your model. So this takes a lot of like self-discipline, right? Don't run your conceptual model first. Run the conceptual model plus the conceptually omitted or deleted paths. Okay, so I run this model. What are the degrees of freedom for this model? 0. So what's the chi-square going to be? 0, right? I'm not going to get any kind of test of model fit. So you might be thinking to yourself, well, why the heck do I want to do this? I mean, it's kind of silly. Like there are 0 degrees of freedom. I don't get any test of model fit. So what is this model telling me? Well, again, here at step 1, I'm not going to look at all of the paths. I'm only going to look at the paths that I think that I don't need. And so I'm going to look at those 3 paths I think I don't need. And I'm going to say, is that true? After controlling for all the things that I think I need, can I really eliminate the paths that I don't think that I need, right? So it's like this test of your own logic, but it's done in a very systematic way, right? So it's like, okay, do I really not need these 3 paths? And so in this case, when you're doing this step 1, you're just looking at those 3 paths, and because your conceptual model is your baby, you're rooting for those 3 paths to not be necessary. And how am I going to determine lack of necessity? I mean, well, one of the most common ways is just traditional statistical hypothesis tests, right? So if these paths are not statistically significant, then I don't need them. If they are statistically significant, I do need them. I mean, I would encourage you to go a little bit beyond just, I mean, you should think carefully about 2 things. One is what's the right alpha level for these tests, right? And I would argue, and again, I think it somewhat depends on sample size and things like that, but you might want to set a more stringent alpha level here, right? Like, you know, if you've got 10,000 people and the p-value for one of these paths is 0.048, like, I don't know, is that really compellingly a necessary path? You should also look at effect sizes, right? Like, what is the actual magnitude of the path? Again, if you've got 1 million people, every path is going to be statistically significant. But like, if the standardized regression weight is 0.001 and it's statistically significant, like, is that actually an important path, right? Like all the other paths are 0.5 and this one's 0.001, but statistically significant. Do you really need to leave it in there? No, probably not. So I would encourage you, don't be just a slave to p equals 0.05, less than 0.05 in, greater than 0.05 out. Having said that, that's what I'm going to tell you to do for homework, because this isn't really like this. Well, I mean, because it isn't really your data, right? And so I want us all to use the same logic so that it's easier for us to correct it. But like when it's really your data, and if I want you to do something else, I'll tell you what the logic is. But when it's really your own data, I really think you want to think, what's the appropriate alpha level? Is 0.05, right? Is that the right alpha level or not? And also, you know, because I want to minimize type 1 error in some sense here, right? I don't want to like add paths I don't need, right? And then the other thing is think about effect sizes. Now, you know, again, we're all living in sort of, you know, sort of the era of open science and pre-registration, right? And so this is something that's very easy actually to pre-register. You say like, this is how I'm going to build my model. I'm going to use these steps. At step 1, I'm going to test my conceptually omitted paths. These are the criteria I'm going to use. Anything that has an effect, you know, anything that has a, you know, a p-value above this or an effect size below this, I'm going to, whatever, however you want to say it, I'm going to consider to be not necessary, right? I'm going to call that like, you know, close enough to 0 to not matter, right? Okay, so that's step 1. I'm only going to look at those paths. I'm not going to look at my specified paths. Any of the paths that I determine I need from step 1, I'm going to keep in the model for step 2, the test of specified paths. Any of the paths that I determine I don't need in the model, I'm going to drop before step 2. So if you were right and those 3 paths are unnecessary, then step 2, the test of specified paths, is going to be your conceptual model. It'll be one and the same. But let's say one of those 3 paths does turn out to be necessary and 2 of them don't end up being necessary. The test of specified model, test of specified paths is going to fit the conceptual model, but it's also going to include any of the conceptually omitted or deleted paths from step 1 that you determined you can't actually delete. The ones you wanted to delete, but it turns out you can't delete, are included in
Betsy?
step 2. Yeah.
So are you saying in step 1 that we test a model with only, because when you said just identified, I assumed that all the specified paths would also be in it, but you're saying only the ones we would have omitted and not the,
No, that's good, Hannah. No, what I'm saying is they're all in there. I mean, the model is a just identified model, so it includes all of the paths, but the only paths that you're looking at this point, so you get the output, you've got parameter estimates for all of your conceptual paths, you just don't even look at them. You don't care about the parameter estimates for your conceptual paths, you only look at the parameter estimates for the paths that you think that you can omit. Why is that? Why am I saying that? Well, because the model from step 2 is going to be the model that you're actually going to interpret. And it is possible, right? It is possible that maybe when you add those conceptually omitted paths, let's say you have a conceptually omitted path that even though it's not statistically significant, you are now, right? You have that linkage. And so one of your conceptual paths are not going to have the exact same magnitude that they would if you didn't have that path in there, right? So you don't want to look at any of your conceptual paths until you have the model that you really want to look at. So step 1 is all the paths are in there, but I'm only going to evaluate the ones I think I don't need, which I know sounds really weird at first, but if you stop and think about it, the logic makes sense. So I start with a model where there are linkages among all variables, but I'm only looking at the linkages that I think I don't need. And it's me being sort of tough on myself and saying, I think I don't need these paths. Is that true? Before I move forward and sort of run this model, I better check that. I'll give you an example. Like, let's say that somebody says, I think that I'm just making something up. So let's say I think that SES predicts, that's not a good example, but okay, I think that academic self-perception, here we go. I think academic self-perception predicts motivation and motivation predicts achievement. And I don't think that there's any effect of academic self-perceptions on achievement after I control for motivation. I really think that, yeah, okay, people who feel better about themselves academically, they tend to be more motivated, and people who tend to be more motivated tend to do better. But after I control for motivate, I really believe like academic self-perceptions is important because it predicts motivation, but there's no direct prediction of academic self-perceptions on achievement after controlling for motivation. Let's say that's my model. It's like a simple mediational model, and I think there's complete mediation there. Well, okay, you think that, but is that right? Well, if that's the only model that I try, right, then I'm basically going to kind of be squeezing as much of the effect of academic self-perceptions on achievement as I can through motivation, right? Like as much as motivation, right, as much as I can is going to sort of squeeze through motivation. There may still be some effect of academic self-perceptions on achievement that can't be explained by motivation, but I haven't put that path in, so I haven't looked, right? I write up my paper and I say to the whole world, hey, after control, academic self-perceptions is only important because it affects because it predicts motivation. And once you know about motivation, you don't have to worry about thinking about academic self-perceptions because that's all you really need to know is how motivated they are. But I didn't actually look to see if that's true, right? So that could be just absolutely false. That could be wrong. Even though I believe it, even though that is my theory and I'm sticking to it, I should be my own worst critic and double check before I start telling everybody that, you don't need a direct effect for academic self-perceptions that like, yeah, well, it doesn't matter once you know about motivation. You should make sure that's true. Yeah.
So my visceral reaction to that is that you're letting the data lead instead of theory. And so I'm trying to understand.
There's a place in the world for theory. Theory leads my conceptual model. There's also a place in the world for data. Like anybody who lets theory drive them and just says, data set after data set would suggest my theory is wrong, but I'm sticking to it because it's my theory, darn it. That's a problem, right? So I think there's a place in the world for theory and there's a place in the world for data. So I don't think I'm letting the data drive the theory. I have a theory, I have a conceptual model, but I'm also saying, you know, I should, before I go out on a limb and say, I have data that support my theory, I better make sure that my data support my theory. That's what I'm saying. Does that make sense? I know. People, you're not the only one who's probably had a visceral reaction, but I think it's important to remember that each of these things have a place. I am not saying take your data, fit it any which way that gets you the best fit. That would be really problematic. That would be more problematic than the first thing I told you not to do, which is just fit your conceptual model and go with it. So yeah, I mean, you have to have a theory. Everything you do in this class has to be driven by theory, which is hard when you teach this class because you don't have theories for any of the homework problems. So you're going to kind of fall back on some basic, you know, guidelines that I give you for this class. But underlying all of this is theory. But you also, you know, you have to have a theory that you think, like to advance sort of theory and science, we have to have a theory that we think is potentially falsifiable, right? And then we have to sort of, right, see if it holds up. And that's the science is just sort of this, like this process of sort of continually refining our theories as we learn more. And we learn more often from data. Yeah.
So does it ever happen that when you're looking at the just identified model, that actually both pathways, one that you weren't planning to emit becomes insignificant because of a high degree of covariance between the two factors? And in that scenario, what would you do? Would they represent a latent factor, like a common latent factor, or because the suppression effect?
So I think what you're saying is, could it be that you have two paths you think you need, but because they're so highly correlated with each other,
Or a path that you think you need and a path that you don't think you need.
okay.
And their intercorrelation kind of suppresses the direct effects.
I mean, theoretically, that could happen, right? So, I mean, again, I think that's I feel like we'll get into some of those issues more when we get into the latent variable modeling part. Right now, we're just talking about observed variables, but yeah, I mean, so what should you do? I mean, I think it's really important. I guess this is sort of another step back, but before I ever start running any kind of models, path models, confirmatory factor analysis models, hybrid structural models, whatever, the first thing I do is spend a long time, you're not gonna like this, sorry, looking at my correlation matrix. That's data, I know, but I think it's really important to get a sense of the data at hand. And because everything we do in SEM is a function of the variance covariance matrix, looking at the correlation matrix can give you real clues about whether you're going to have those kinds of problems. And like the more you do this, the more, I mean, I'm at a point where I can like somebody comes in my office and they want to talk about their model. Usually the first thing I'll say is like, you know, after they talk about their model and their theory and everything, I'll be like, let me see your correlation matrix. Let me look at the correlations, you know? I mean, I can look at a correlation matrix usually and tell you how many factors you're going to get, you know, which items are going to be on which factors. And I mean, you just like, you get a sense of it. So yeah, I mean, all of the issues that you've talked about in multiple regression, suppression and collinearity and all of those things are potentially problematic. I think a good first step for sort of dealing with that is really understanding the covariances, or I mean, again, covariance is hard to look at because they're unstandardized. So the correlations among your variables. And I think, you know, what the right answer for that, I don't want to give sort of a rule of thumb because I think it's going to depend on what model you're talking about. What, you know, like what does the model look like? What do the variables look like? What do the paths look like? But yeah, yes.
Yeah, in a step one, what if it turns out that one of the paths we thought is important isn't actually statistically significant? Should we delete it in a step two?
Yeah, so we're not going to look at any of those paths we thought were important in step one, right? So that's kind of my point, is like all of the paths you thought you needed in step one, you don't even look at them. You just look at the ones you thought you didn't need. Okay, so now let's go to step two. So step two is going to be my conceptual model with any of the omitted paths that it turns out I do need. And it's in step two that I'm going to look at my conceptual paths, right? And now I'm going to determine whether all of those are necessary or not, right? So I'm not really going to look at how well my conceptual paths are performing until step two. Because, yeah, so step one is look at the paths you think you don't need, right? Then keep any of the ones you thought you didn't need that you actually do need. Move to step two. Step two is the conceptual model plus any of the paths it turns out you needed. And there, I mean, for sure, the conceptually omitted paths are going to stay because they already stayed, right? And then now you look at your conceptual paths and you determine whether all of those conceptual paths are actually, contributing, right? Are they all, what is, again, are they statistically significant? What is the magnitude, etc. And now you can either stop at the end. I mean, obviously you're going to evaluate all of the paths. You can either stop at the end of step two and just sort of evaluate the paths. And if it turns out that one of your conceptual paths isn't necessary, you keep it in the model anyway. And you just sort of talk about that in your, in your results section and say, this is what this is how I built the model. This is what I found. Turns out, let's just make something up here for a second. Oops. Let's go back. Let's say, imagine, turns out I do need a direct path from motivation to GPA, right? And I don't need a direct path from, I don't know, academic self-perceptions to GPA, whatever it is. I mean, you would talk about that in your results, but you'd actually stop after step two, and that would be your final model. Or, and this is totally optional, and it really, I think, depends here on the field and the journal and the model. It depends on a lot of things. But step three could be to trim the model, to get rid of any non-statistically significant paths, which in this case are going to be non-statistically significant conceptual paths, right? So some people like to do that. Some people don't like to do that. I mean, I think there are pros and cons. I don't really have a strong feeling. I do think it depends in large part on the context and how sort of unwieldy how big the model is and all kinds of things. But so again, in your own research, that's a completely optional step, and you should go by sort of what others in your field do. In your homework assignment, I think I'm going to tell you to actually do step three, just so you have the practice of going through steps 1, 2, and 3. Yeah.
And so if you're wrong, you're like initial conception,
Mm-hmm.
so it's one for sure, but multiple of your omitted paths actually didn't be there. How do you talk about
I was wrong, right? I mean, I hypothesized that. I mean, that's right. That's how it is with hypothesize this, and it turns out that. I mean, I think that's always the challenge, right? Is sort of then, telling that story, obviously. But I mean, I think you are always upfront about it. This is what I thought. This is what I found. Now that this is how I feel like this is how it always goes in research, right? This is what I thought. This is what I found. Now that I think about it, that kind of makes sense, right? I wasn't thinking that before, but now that I think about it, I can kind of see why it might have happened that way. And then, boy, somebody should probably get some more data and check this out again, right? And see if it holds in a new sample. Yeah.
So I think in one of the textbooks it was saying that it's always good to have backup models to test as well. So where would that kind of rationale fit in with this, or would this be?
Well, in some sense, this is step one is a backup model, right? I mean, it is good to have. It is. We haven't gotten into this idea of testing competing models, but one of the really cool things about SEM is that you can actually, I mean, these are, like right now, we're just talking about a set of nested models and sort of a logic for making sure that you're not overlooking something important in your model building. But it is true that like you might think that it works this way, and somebody else might have a very different theory about the way that these variables relate to each other, right? And one of the cool things about SEM is that you can actually test competing models. Sometimes those competing models are nested, and that's really nice because then we can actually do these chi-square difference tests and we can sort of directly compare them to each other. Sometimes the models aren't nested. We can still compare them to each other using measures of model fit, you know, and some other sort of guidelines. So, I mean, I think it's always nicer rather than just sort of throwing out a model and saying, like throwing out a model, fitting it and going, eh, looks good enough, you know, this is my model. I think it's always nicer if I mean, in cases where there are two competing models, it's nicer to be able to run those two models against each other and say, oh yeah, this is actually with these data, this model appears to, you know, this model appears to fit the data better than this model, right? So, you know, again, will that be the case with another set of data? I mean, it always takes more than one study to get a definitive answer. So I think it's good to remember that as we do this. But yeah, so I mean, if you have conceptually competing models, I think that's where you would probably do that after step 2, right? So I would still do steps 1 and 2, and then you might actually branch out and say, okay, well, this research team though looks at it completely differently, and we also fit their model, and lo and behold, our model fits better than their model, right? Or whatever. So yeah, I mean, I think that's a huge strength of SEM is that we can test competing models. But yeah, I would fit it in sort of in step, probably after step 2. I would still, even if I had competing models, I would still, for my own model, want to do steps 1 and 2. I think there was another question. Yeah.
If parsimony seems to be the goal, I don't understand why step 3 would be optional.
Yeah, okay, question. If parsimony seems to be a goal, why would step 3 be optional? Yeah, I mean, yes, I agree. So parsimony is often a goal, and we don't necessarily want to keep in a whole bunch of extraneous paths that we don't need. On the other hand, I mean, you know, the world is gray. It's not black and white. And so, like, you know, is this a p-value of 0.048? Does that actually mean that this path is not important, right? And does a p-value of 0.051 mean that it is? You know, right? I mean, so I think one of the reasons that people don't trim out non-statistically significant paths is actually for other researchers, so that, because like when you trim them out, yeah, you're saying, okay, it wasn't statistically significant, but others reading the article might be like, yeah, okay, but like you had a kind of a small sample size, maybe, let's just say, and I'd really like to know what the magnitude of that coefficient was, right? And what's the confidence interval for that coefficient? You're telling me it's not statistically significant, but you've trimmed it out, so now I can't see anything. And I'd really just rather know that the parameter estimate was 0.03 and the confidence interval went from negative 0.03 to positive 0.09. Like, I want to know that information. And if you trim it out, I don't know that, right? And so, like, not statistically significant could look different in different scenarios, right? And I think it's really to give other researchers more information about what that, I mean, you can still say like this path doesn't matter, but if you keep it in there, you're giving information about what that, your conclusion that it doesn't matter, what does that conclusion it doesn't matter really look like? If you trim it out, people are kind of left to guess a little bit. Although, like, a solution to that I often will use if I trim things out is to actually present the parameter estimates from the multiple models so that people can actually see it. So you present the final trimmed model, but they can actually see the step 2 model. So then you actually, in my mind, that's kind of the best of both worlds, because people can look back on the path that you deleted and see what is how big is the parameter, what was the confidence interval like, right? Did actually trimming that parameter out, did it actually change appreciably any of your other parameter estimates, because that's another thing, right? Like you should, if these, again, if you have a decent sample size and you start trimming paths out in step 3, it shouldn't really change the parameter estimates that you leave in. It really shouldn't. So from that perspective, it seems nice to be parsimonious and trim them out. But if you only present model 3 with everything trimmed out, again, the sort of skeptical reader is left to wonder, well, what did the model look like when they were in? Did it really look just like this? So, I mean, being able to sort of show what the parameter estimates were before and after trimming, I think is really nice, because again, in step 3, the trimmed model, the paths you leave in should be, well, they're not going to be identical, but they should be really close, right? They should be like not different enough to make a difference between the step 2 paths and the step 3 paths. Anyway, other questions? Yes.
Comment. So it seems to me, so classically, like null hypothesis studies aren't published, right? We don't know what didn't work. So this is like an alternative better model of kind of being able to see what worked and didn't work with more information.
Yeah, right. I mean, I think our goal, is, and I mean, I guess you're right. Null hypotheses are often not published, and that's bad news. But I guess one good thing about SEM is you're unlikely to get a completely null model, right? You're unlikely to have a whole model and have everything be non-statistically significant. So you're sort of guaranteed to probably find something. But you're right that, I mean, I think our goal is to have a theory, super important, be our own, but also sort of set up a situation where we are systematically being tough on ourselves and our theory, and hoping that the theory will withstand our sort of tough self-critique, right? And then always knowing that, like, again, this is one data set. This is, whatever we find is not necessarily going to be, no one study finds the truth, right? But yeah, so I think that's kind of the logic, is that we want to be sort of systematic in our building of the models, in our testing of the models, and in our reporting of the models. And we want to give people as much information as possible so that they can assess what we've done. And that's the other thing about being systematic. And again, I feel like things are getting so much better. Like in the last few years, people are being more responsible about reporting results and things than they used to be. But, people just kind of present models, and you didn't know how they came up with the model, how they decided what paths were in and out, whether they tried 15 other models before they settled on this one because this is the one that they got to fit the best, And then it's really, and of course, if you sort of go in and you just start messing, around and sort of just letting empirical, like just being totally empirical in your decisions, you're not going to get a model that's replicable. And there have actually been some really interesting simulation studies that were done 20 plus years ago, where people looked at, okay, we haven't talked about this yet, but there are these things called modification indices that say, hey, if you added a correlation here, if you added a path here, your chi-square would drop by this much. So your fit is going to look better. And so some people did some studies about, like, what if you, like, they simulated the true model, right? And then they said, what if you sort of ran a base model and then you just started using these modification indices, which are these things that come out automatically in the output, to guide, like, where you start, how you modify the model. So let's say you just do it completely empirically, just to try to get better fit. And the answer is you don't actually get the true model out. You end up going, that doesn't work. It doesn't work. So we need a systematic way that stays true to our theory, but also allows us to not get blinded by our theory and say, like, well, of course I'm right. I don't even need to consider any other options, right? Okay. All right, ready to move on? Okay, so this is pretty easy, right? Where are the deleted paths here? Where are there not paths that there would be paths in a just identified model?
X1 to Z,
Yeah, x1 to z and x2 to z. And so to turn this into a just identified model, I would just add a path from x1 to z, and I'd add a path from x2 to z. And I should have said, I mean, we got sort of on a tangent, but let me just emphasize that when we do this, we want to turn our model into a just identified recursive model. So in a recursive model means, right, that, sort of anything that is, sort of downstream, right, anything that's sort of an effect is not then going to become a cause of something that's further upstream. So we don't have feedback loops. Now, technically, recursive, any model that has feedback loops of some sort, so like if I had z, let's say if I had z predicts x2, that would now be a non-recursive model. So when I create the just identified model, it's really clear that the pathways need to go from x1 and x2 to z, not from z to x1 and x2, because that would turn it into a non-recursive model, which we haven't talked about yet, but there are more complications to think about when we estimate non-recursive models, and that model wouldn't be identified, even though it would have 0 degrees of freedom. So we're always going to turn these into recursive models. All right. Okay, so I think I said all this. I said step 1 is test the conceptually omitted or deleted paths, right? We're going to make it a recursive model. Occasionally, we might make it what's called a block recursive model. A block recursive model is technically not recursive, but it has, oops, sorry about that. It has correlated disturbances between two variables that are sort of at the same level. Let's see if this will work. So imagine I have something like this. So let's say I've got A, B, C, and D, and of course there's some disturbances here. Okay, so I've got A, B, C, and D, and I don't right now have a linkage. I don't have a linkage between A and D, right? But I don't have a linkage between C and D. And this is what I mean by like they're at the same level here, sort of, right? So I'm saying B predicts C and B predicts D. So there are 3 different ways that I could make a linkage between C and D. One would be to say C predicts D. One would be to say D predicts C. And one would be to say that the disturbances of C and D are correlated with each other. Now, as soon as I say that the disturbances of C and D are correlated with each other, that's actually not a recursive model anymore, right? Because the way I defined a recursive model is a recursive model has, no feedback loops, right? No sort of looping back on itself in any way, and it also has no correlated disturbances. But this is what's called a block recursive model. And again, we'll get into this more when we talk about non-recursive models. But it's called a block recursive model because even though it's non-recursive, you can sort of think of these as almost being like blocks in a chain. And with the, it's recursive across blocks. So yeah, there's this correlated disturbance here, but that doesn't actually, if you think about the tracing rule, it doesn't actually like backwash into B or A. And so because they're sort of at the same level, it doesn't actually, in this case, matter whether you say C predicts D, D predicts C, or C and D, the residuals of C and D are correlated with each other. When I say it doesn't matter, I don't mean that you're going to get the same parameter estimate for that deleted whatever you put in. You're not, right? Just like in regression, if you say Z predicts Y, you're not going to get the same regression coefficient as you do if you say Y predicts Z, right? And those aren't going to be the same as if you allow for that correlated disturbance. So the parameter estimate will be different. But given that it wasn't something you thought you needed, in some sense, you don't have to sweat it too hard. I would do whatever sort of seems like it makes the most conceptual sense in that case. And any one of those will give you a just identified model. So does it conceptually make more sense for C to predict D? Does it conceptually make more sense for D to predict C? If it's really not clear that either of those make conceptual sense, then it makes sense to just allow the disturbances to be correlated. And any one of those three will give you a just identified model. And so this is why I'm like really, so make it a recursive model, or it can be a block recursive model in the sense that you can allow the disturbances to correlate between two variables that are, again, sort of in the same block. So that, again, sort of, you don't have any, I'm going to call it like backwash. You don't have any backwash back into either A by doing that.
So block
Yeah.
recursive model is just about the correlation between disturbance is just at the last block. I mean, is that possible that we have some other variables after C and D and again?
Yeah, that's a really good question. So the question was, does this mean you should only do that for the last block because you correlated the disturbances for, let's say, if there were a B and E, let's say, right? So now I've got a disturbance here, right? Does that, could I correlate these disturbances? And the answer is, yeah, you could. You could do that. And if you sort of, again, if you work it through, you're going to get the same model implied correlations no matter what. Because again, that correlate, now it's true, right? That it is true that they're right. I've created this sort of pathway where, okay, so the disturbance of B is correlated with the disturbance of E, right? And then if I were thinking about doing model implied correlations, I could trace through like that. Absolutely true. But I mean, again, if you think about it, if I put a pathway there, I'm also going to have a linkage that flows through, right? So that's not gonna be problematic necessarily. Yeah.
Is there a reason why with exogenous variables we allow the observations to covary, but then when we're talking about endogenous variables, you switch it to correlated disturbances instead of correlations between the actual observations?
Yeah. Yes. So the question is there a reason that we switch to correlated disturbances once variables are endogenous instead of just thinking about correlations among variables when the variables are exogenous? Okay, now let's take another variable here that's like H. Okay. Oops. Maybe I'll do the little thing. So remember that with exogenous variables, there's absolutely nothing predicting H or A, right? So they're sort of like on the outside of the model, not looking in, because they are part of the model, but they are only predictors. They are not predictive. So there's no way to get a disturbance variance, right? Because this is a variable. It has a variance. I think this variable influences other variables. And for sure, in the greater world, there must be something that influences this variable, but I just don't have it in my model. So in my model, this variable is only a predictor. It's not ever predicted. And so I'm not partitioning this variance into different pieces, right? But now when I come to B over here, B is an endogenous variable. It's a predictor, but it's also predicted by A. And so when I estimate my model, I'm not actually estimating the total variance for B. I'm partitioning the variance into two pieces. One piece of the variance in B is the piece that's explained by A, right? And the other piece of the variance in B is the piece that's unexplained by A. So instead of estimating a total variance for B, I'm saying like some of the variance in B is explained by A, some of the variance in B is not explained by A. If I take those two variance sources together, the unexplained variance plus the explained variance, that's going to give me the total variance. But I'm not estimating the total variance as a parameter in my model. I can like reproduce it. I can recreate it from the parameters I am estimating. But for every endogenous variable, I'm estimating, I basically say, hey, how much of the variance can I explain? How much of the variance can't I explain, right? Like how much is predicted by all these different other variables, and then how much of the variance is left over that can't be explained by the other variables in my model. And by taking all that and putting it together, I can actually come up with what the total variance is, but that's not a parameter. Here, nothing predicts it, so I can't do that. So what I have is the total variance. So I'm starting with the total variance here and using it to predict other variables. Does that make sense?
Yeah, thank you.
Sure. All right. So, okay, so we said all these things about step one. So here I'm just showing you what the conceptually omitted paths would be, right? So what we would do here in step one is, even though my model doesn't include these paths that are sort of in, red dashes, step one model is actually going to include those conceptually omitted or deleted paths. And then when I get the results from step one, that's all I'm going to look at. I'm just going to look at those red dashed paths and say, do I need those paths or not? And then in the test of the specified paths, I'm going to retain either of these or both if it turns out that I needed them from step one, right? So if I need those conceptually omitted paths, I'm going to leave them. If I really was right that I don't need them, I'm going to eliminate them. So keeping any dashed paths that were necessary, and we haven't run it yet, so I just kept them both in there, but of course we'd eliminate either one that we don't need. Then we test the conceptual paths of interest, the A, B, and C paths. So we run the model with any conceptually omitted paths included, and then we look at the conceptual paths of interest. And again, in step three, the trimmed model, I would drop paths that were theoretically specified but not statistically significant from step two. And there are lots of ways that you can actually think about tests of paths, and we'll get into this a little bit more as we go along. But you could think about just looking at the individual paths, right, with some sort of a standard F or T test. You could think about doing almost like a multivariate test, like simultaneously testing all of the paths that you don't think you need, which would be like an F test for all of the paths. Or what I'm going to argue is probably the best way when we want to look at multiple paths simultaneously is to do a combined test of all the paths in the model using chi-square. So we can actually use, we'll talk about this more, we can use something called a chi-square difference test to compare the fit of the model that includes some paths with the fit of the model that excludes multiple paths. So we don't have to just rely on looking at things sort of univariately, one path or parameter at a time, but we can also look at multiple parameters simultaneously and compare the fit of two models where multiple parameters are constrained by using the chi-square difference test or the chi-square test. So we're going to talk more about that as we go along today. Yeah, I think I've said all of this actually. So I'm going to skip this, but we've already talked about it. Okay, so now let's talk about nested models. And this is important and kind of complicated. So some examples of what models are nested are really quite easy, but sometimes it can be really difficult to determine whether two models are nested. So actually in a couple of weeks, I'm going to give you a way to determine whether really complicated models are nested or not. That's sort of a bit empirical in case you ever get stuck and you can't tell. But for now, let's keep with like kind of simple examples of nested models and the general principle. So the general principle is a nested model, and this is important. So for two models to be nested, you have to first be starting with the same set of variables, okay? And you have to have the same sample, same number. And of course you can have the same sample, but like you need to also have the same sample size, right? You need to have the same cases. And that's important too, because sometimes, it's not going to happen so much here in SEM because we're working with the variance covariance matrix. So if you're working with one variance covariance matrix, it's sort of staying constant, right? But like, there are times where sometimes when people, change models, that might actually change the sample size. So it's important if you're thinking about nested models that you're talking about the exact same observations and you're talking about the same, in our case, it's the same variables. So it uses the same variables, and the easiest way to sort of think about nested models are, nested model is a model that uses the same variable, same variable, same number of cases as another model, but it either is adding one or more additional parameters, or again, because there are two models we're comparing, you could say conversely, it could start with this model and it could be constraining one or more paths. So in that case, there are two models. One is a simpler model and one is a more complex model. So the simpler model is the model that has fewer parameters, and it has, because there's fewer parameters, it has more degrees of freedom, right? So, and I mean, by the time the semester is over, you're going to be sick of hearing me say these things in combination. But just for now, remember, a more parsimonious model, which is a simpler model, you're estimating fewer parameters. Because you're estimating fewer parameters, you have more degrees of freedom, okay? And because you're estimating fewer parameters and you have more degrees of freedom, and it's a more parsimonious model, your chi-square is going to be higher. And actually, we're striving for a low chi-square. So the fewer parameters you estimate, the simpler the model is, the higher the chi-square is going to be, right? And the more parameters you estimate, the lower the chi-square is going to be. The lower the degrees of freedom, and the lower the chi-square is going to be. And if that makes sense, if you think about the fully just identified model, which is fully parameterized, right? We have 0 degrees of freedom, and we have a chi-square of 0. So like the lowest the chi-square can ever go is 0, and that's when we have 0 degrees of freedom, which really means we're estimating as many parameters as we possibly can. So as we make simplifications, we're adding degrees of freedom, we're making for a more parsimonious model, but the chi-square is going to go up. And the question is, yeah?
Sorry, I wanted you to finish your thing, but I have a question when you're ready.
Okay, so the question here is, okay, sure. So I'm deleting, like I'm constraining parameters, right? I'm saying, because remember, every time I delete a path, what I'm really saying is I'm constraining that path to be 0. I'm constraining that direct effect to be 0. So I'm making constraint on the model. So every time I do that, right? Every time I make a constraint, the chi-square is going to go up. It might go up, like it might be basically identical, right? It might be, you might not see a change at all. The chi-square might be basically the same between the two models. Well, if it's basically the same between the two models, that means that eliminating that path or constraining that path to be 0, it didn't hurt the fit of the model, right? Like imagine I started with a just identified model, and then I eliminated one of those conceptually. Imagine I start with a just identified model, and I eliminate those 3 conceptually omitted paths, right? And remember, the just identified model is going to have a chi-square of 0. So imagine that I eliminate those 3 paths, and let's say the chi-square goes up to 2. Okay, so it's not 0 anymore, but it's really low, right? So the chi-square only increased by 2 by eliminating 3 parameters. So we would say, well, that's not much of a change. Those models fit about the same. But hey, the one model, I got rid of 3 parameters, and it still fits about the same. I mean, obviously, if I eliminated those 3 parameters and the new chi-square was like 0.001, you'd be like, that's basically 0, right? So then the question is, how big a chi-square change suggests that, really no big deal, versus how big of a chi-square change suggests that, well, maybe we need that parameter. Well, we tend to use, when we do the chi-square difference testing, when we do a chi-square difference test, we compare the chi-square of the 2 models. So let's say I have a chi-square, let's go with my model. So chi-square for the first model with 0 degrees of freedom had a chi-square of 0. My second model has 3 degrees of freedom because I eliminated 3 parameters, and the chi-square is 2. So I can say, okay, the difference between the chi-squares is 2, And the difference between the degrees of freedom is 3. So by eliminating 3 parameters, the chi-square only went up by 2. What I'm going to do is I'm going to compare that difference in chi-square to the chi-square, the critical value of chi-square with 3 degrees of freedom. Why 3 degrees of freedom? Because that's how many parameters I eliminated. So I bought myself 3 degrees of freedom. So you can actually go back to the chi-square table and say, okay, what's the critical? I should know this, right? I should always use 1 and 2 degrees of freedom. You might catch me on 3 degrees of freedom. What's the critical value of chi-square? Well, what's the critical value of chi-square with 1 degree of freedom? Let's start there. Who knows? I should have like candy to throw so people can get this right. What's the critical value of chi-square with 1 degree of freedom? Nobody knows? Somebody knows. I know Jocelyn knows, but somebody else. Okay, this is like a little piece of statistics trivia for you. And you'll never forget it once I tell you. So the chi-square distribution with 1 degree of freedom, I'm looking at making it look like that, but that's actually a normal distribution. It doesn't look like that. A chi-square distribution with 1 degree of freedom is actually the same as the distribution of z squared. So you remember the z distribution, the normal distribution, right? Where we have like, standard normal, we've got a mean of 0, standard deviation of 1, blah, 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 right? Okay, so if you basically square z's, that will give you the chi-square distribution with 1 degree of freedom, which if you think about what that looks like, then you start with like the z distribution, like a normal curve, and imagine if you square it, then all of these numbers that were negative are now going to be positive. So I can't really draw this well, but basically this part is going to fold back on this part, right? And so you're going to end up with a distribution that doesn't go below 0, right? And it's going to be really, again, this is really not a good drawing, but it's look at a picture of a chi-square distribution of close. You can see what it really looks like. But it sort of looks like this. And really what it is it is the distribution of z squared. So what's 3.84? Well, it's 1.96 squared. So the critical value of chi-square with 1 degree of freedom is just, remember the critical value of z, right? At 0.05 is 1.96. So the critical value of chi-square with 1 degree of freedom at 0.05 is 3.84. It's just z squared. So it's easy to remember. Or if you forget, you can just take 1.96, you can square it, and you'll know what the critical value of chi-square is with 1 degree of freedom. Now, chi-square changes shape. The chi-square distribution changes shape as you get more degrees of freedom. It gets less leptokurtic and less positively skewed as you increase the number of degrees of freedom. It's still not going to go below 0, but it'll sort of get increasingly sort of looking more like a little bit of a lopsided normal distribution. So chi-square with 2 degrees of freedom, the critical value is 5.99. That's a really easy one to remember. 3 degrees of freedom, I believe, is 7.82. So you should double check me on that, but I think it's 7.82. It is? All right, good. Beyond that, I usually have to go to the critical value table myself, but there's also another really good rule of thumb, which is if you get enough degrees of freedom, the critical value of chi-square is just a little bit more than the degrees of freedom. So I don't know what the critical value of chi-square with 100 degrees of freedom is, but I know that the critical value is a little bit more than 100. So if I run a model and the chi-square is 100 with 100 degrees of freedom, I know that chi-square is not going to be statistically significant. It's not going to actually exceed the critical value. Now, if you told me your chi-square is 120 or 110 or 115 with 100 degrees of freedom, and you asked me if it were statistically significant, I would have to go to my chi-square table. But if you told me your chi-square is 100, I could say, no, it's not significant. If you tell me it's 200 or even 150, I know it is statistically significant. So it's just going to be just a little bit more than the degrees of freedom if the chi-square gets higher. Okay, now I've digressed, and I feel like poor Hannah has probably forgotten her question, but what was your question, Hannah?
I have not forgotten, and it was still helpful. So my question is a lot simpler than all the chi-squared stuff, which is just clarifying for myself that when you say adding parameters, that can really only be paths, right? Like it's not like we can add disturbances or error terms because those have to be there, right?
Yeah. It's not just paths. It could also be correlations or covariances.
Oh, right, the covariances. Yeah, I just mean like arrow things.
But you are right that every endogenous variable is gonna have a disturbance, and every exogenous variable is gonna have a variance. So yeah, I'm not actually talking about adding variances or disturbances. We could add a correlation between disturbances, as we talked about, but no, we're not talking about adding disturbances. I will say this: there are lots of ways to make constraints on models. Right now, we're really thinking about adding and deleting paths and correlations, but there are other ways you can make constraints. So you could, for example, I could say, and again, you got to think about whether this makes sense, right? I'm just showing you things you could do. I could say these two paths, the paths from E and B to D, are constrained to be equal to each other, right? That's another way. So that's not actually saying that one of those is 0, but what I'm saying there is that the difference between the two of them is 0, that they are equal to each other. So if I say that these two paths are equal to each other, then I've actually bought myself 1 degree of freedom, right? Because I'm only estimating one path instead of two paths. So that's like another, and again, we'll do more examples like that as we go through the semester, but that's another way to make a constraint. There are other things you could do, Hannah. You could, again, most of the time you're not going to do this, okay? But you could, and there are times when it makes sense, you could say, like, I want to constrain the let's say I have H and A over here on my model are both exogenous variables. I could say I want to constrain the variances of H and A to be equal to each other. Why? Well, I don't know off the top. I mean, like when it makes sense, you'll know it. I mean, there are actually times where that might make sense. Or I could say I want to constrain the disturbances of C and D, these endogenous variables. I want to constrain the disturbance variances to be equal to each other. So again, that buys you a degree of freedom because you're only estimating one disturbance variance instead of two. You'll see that we do this a lot actually in measurement models. We'll do things like this quite a bit. So there are lots of different ways that we could think about sort of making making simplifications. But again, most common, we're constraining some path or some covariance to be 0, or we might be constraining two parameters to be equal to each other. Yes.
In the homework, we had an item around under restricting or under identifying. That was the CFA. So with a structural path, can you under identify as well?
Well, you can, but remember, if a model's under identified, you can't run it, right? So you're right. There was a question about under identification in the homework, but I just want to be clear that that's not an okay model, right? Like, yeah, I could draw it, and I want you to be able to recognize it's under identified, but because it's under identified, that means you can't estimate it, right? So could I draw an under identified model here? Yeah, I could do an under identified path model here. Hold on, let's go back to our picture here for a second. I should try to. Okay, so here I've got a just identified model. So what if I decided that I wanted to not just, what if I decided I wanted to, I also built in, and this would be bad too, because it would also be non-recursive, but which I told you not to do. So, but you shouldn't do this anyway. But so what if I put a correlation between the disturbances of U and V? So now I actually have two linkages between Y and Z, right? So like, yes, it's non-recursive and that makes it complicated, but even putting aside the non-recursive nature of it, forget about that for a minute. If I did that, what would my degrees of freedom be? -1, right? And anytime you have negative degrees of freedom, even for a recursive model, if you've got negative degrees of freedom, you're going to be under identified. So basically with a fully recursive model, as long as you don't have negative degrees of freedom, you're actually going to be in okay shape. With non-recursive models, even if you have positive degrees of freedom, you can be under identified. That's why they get more complicated. But with any model, Recursive or non-recursive, if you have negative degrees of freedom, you're not going to be able to estimate the model. You're trying to estimate more unknowns than you have knowns. And it's just like trying to solve, it's just like analogous to trying to solve a math problem where you have like x plus y equals 3, right? Like you can't solve that problem with just one equation, right? Because there are like, you know, there's no like single solution or even single, I mean, forget about single solution, right? Like, you know, it's like the possibilities are infinite. It's an under-identified problem at that point. But if I say x plus y equals 3 and x minus y equals -1, let's say, now you can easily solve that problem. That's just identified, actually, right? That's a good example of a just identified, where the number of knowns equals the number of unknowns. And of course, we're going to be working in a space where we're over-identified. So we have more knowns than unknowns. But yeah, we're never going to be able to solve problems where we have more unknowns than knowns. All right. Hannah, did I answer your question?
You did, yes. Thank
Okay.
you.
Good. Just checking. Okay, so we can think about this, the sort of the simpler model, the one that has fewer free parameters, more degrees of freedom, is nested within the model that has more free parameters or fewer degrees of freedom, right? And what I mean by that is I can go by I can take the more complicated model and make some restrictions, right? Make some constraints or restrictions to get to the simpler model. And nested models are, if I can go from the more complicated model and make a bunch of constraints and get to the simpler model, those two models are nested. Or conversely, I can start with a simpler model and free a bunch of constraints, right? Or free a bunch of parameters and go to this more complex model. Those two models are nested. But I can't, and this is very much like a little science problem or science experiment, I can't do both simultaneously and make sense out of it. And it kind of makes sense, right? What if I constrain these 3 things over here, but then I free these 3 things over here, right? In that case, the models are going to have the same number of degrees of freedom. They're going to have different, probably. I mean, suppose mathematically it's possible you could do that and get the same chi-square, but it's highly unlikely. They're going to have different chi-squares, but like you can't then compare them. And even if the degrees of freedom were different, because I make 2 constraints and I free 3 things over here, you can't really make sense of that, because on one hand you've simplified in one way, but you've added more parameters in this other way. How are you going to know what's responsible for the chi-square change? The simplifications, bringing the chi-square up, or the adding more parameters, bringing the chi-square down? So you can't go both directions at once. So that's the most important thing to remember about nested models, is you're going from one model to another by either making it simpler or making it more complex, but not making it simpler in some ways and making it more complex in other ways. That's a no-no, right? By the way, if you want to make a model simpler in some ways and more complex in other ways, you can build a series of models where, maybe you make the you do this model, you make these simplifications, these 2 models are nested, and then you compare this model to this model where you're adding some parameters. So sometimes you can build a chain of models where you have pairs of models that are nested, but maybe the first model and the last model that you fit aren't actually nested, and that's what I'll suggest doing in those situations, because sometimes we will want to do things like that. But in terms of what are nested models, we're just going, we're just going one direction or the other. We're not mixing and matching. And again, I say, if you constrain certain parameters but free others, those 2 models are generally not nested. I say generally because sometimes it's hard to tell when models are nested, because on the surface they don't look nested. But again, it's all about the structure of the variance covariance matrix. So like lurking at a deep level, they might not look nested, but they are, which is why I'm just like hedging my bets. But for now, just think about it the simple way that I said, which is just go one direction or the other. And I'll show you the fancy test for when it's not so obvious in a couple weeks. And that's what I'm saying there. Sometimes it's difficult to determine whether two models are nested. And if we find ourselves in that situation, you know, I'll show you a quick way to do that. Okay. How are we doing? Oh my gosh. Okay. So here's model 1, which is more restrictive. In this example, we actually have a latent variable model, and here's a model 2 that's sort of less restrictive, where those red paths are being added. And these two models in this example are nested models. That's all I'm really showing there. So if two models are nested, then we can test whether the additional complications or sort of the additional parameters of that more parameterized model are necessary. You know, or sort of, again, you can think about it in another way, which is, are the simplifications of the more restrictive or less parameterized model, are they empirically justifiable? Like, can I actually make those simplifications and not, you know, still have essentially the same fit? And the test is a difference in chi-square and the degrees of freedom. So we just look at the chi-square, you know, we just take the chi-square, again, the chi-square of the simpler model is going to be bigger. So the chi-square of the simpler model minus the chi-square of the more complex model gives us this chi-square difference. Okay, and then the difference in the degrees of freedom. So the degrees of freedom for the simpler model will actually be higher, right? Because remember I said degrees of freedom are higher, minus the degrees of freedom for the more complex model. And I'm just going to get the difference in the degrees of freedom. And then I can take this chi-square difference with degrees of freedom equal to the degrees of freedom difference, and I compare that to the critical value of chi-square. Now, if I only have a one parameter difference, so I've only constrained one parameter or freed one parameter, then that should give you something that would be similar to just looking at a, you know, a t-test, right? So like, if it's a one parameter difference and the chi-square test is statistically significant, you know, a t-test or a z-test should also generally be statistically significant. But the advantage of this chi-square difference test is that it also allows us to look at multiple, you know, eliminating multiple parameters simultaneously. Now, if the chi-square difference test is, let's say I eliminate those three parameters from my just identified model, and the chi-square difference test is not statistically significant. So what do we say? Chi-square, the critical value is 7.82. So if I eliminate three parameters from that model and the chi-square difference is less than 7.82, I'm going to say, oh, okay, my chi-square didn't go up by that much by eliminating these three parameters. So the fit is essentially the same. So I can eliminate those three parameters. Great. If the chi-square test is statistically significant, so let's say I eliminate those three parameters and the chi-square change is 20. I'm just making something up. So it is statistically significant. What I don't know when I do a chi-square difference test with multiple, I know that eliminating those three parameters made my fit worse. But it's possible that each of those three parameters sort of contributed equally. Let's say the chi-square is 21, the chi-square difference. So it could be that eliminating each of those parameters caused the chi-square to increase by 7, right? 7, 7, 7. So if I looked at each one individually, they would each one of them be statistically significant if I did a chi-square difference test just for one parameter and another, right? But it also could be the case if you take three parameters as a group and you do a chi-square difference test on those three parameters as a group and the chi-square change is 20, it could just be that one of those three parameters is necessary and the other two are unnecessary. You know, which is why when we do the test of deleted paths, I'm going to argue that we shouldn't just look at the chi-square difference between, you know, the just identified model and the model with the three paths, but we should also look at the statistical significance of those coefficients as well. Because, you know, again, if the chi-square change isn't statistically significant, then we really don't have to worry, right? But if the chi-square change is is big. Again, it could be that we don't actually need all three of those parameters. We may only need one or two of them. So I think it pays to kind of drill down into there a little bit. All right. Oh, so this is what I'm getting ahead of myself again. So this is the chi-square difference test, which we just talked about. So we're always going to favor the simpler model with a non-significant when the chi-square difference test is non-significant, and we favor the more complex model when the chi-square difference test is statistically significant. And again, we can only use this chi-square difference test if the two models are nested. And there'll be lots of occasions where we might be looking at competing models that aren't nested, so we can't necessarily use the chi-square difference test there. All right, this is a perfect place to take a break. So let's take a break for like 10 minutes. You think?
Because you have to wait 5 minutes after.
Oh, well, they won't need to. You should get Hannah started on Mplus. What?
I do have I've already requested access and
Okay.
I have the remote access in already.
Yeah, anybody, and if there's anybody here who's working on a laptop that wants to do a remote access, then you should remote into Mplus during the break. Using the instructions that were on the syllabus, and Jocelyn and I can help you if you get stuck. Everybody else, we're actually going to use the desktop, so we don't have to worry about that. So we'll take a 10-minute break. Anybody who's using a laptop, make sure you've got access to Mplus. Everybody else can take a break, and then when we come back, we're going to do an Mplus. We're going to talk about Mplus and do an Mplus example. Sound good? All right.
Thanks, Betsy. And also, by the way, I am able to hear almost all the questions that people are asking, which is really
Okay.
nice.
Good. That's good to know. I'm guessing you can't see the board very well, though.
I cannot, but I've been able to figure out generally what you're doing, so
Okay.
it's okay.
Sorry about that. Normally, I'd be able to like use it's a little frustrating to have a smart board that's not very smart.
Right.
But with any luck, that'll be fixed by next week.
All right. Sounds good. All right, I'll take the break now. Thank you.
All right, cool. Sounds good. See you in 10. I'll take the break now, too.
I was going to think last week, but I was not glad. I didn't know. Thank you. Yeah. So like, I'm glad I had hopefully over the years, so like stuff like this gets a lot of stuff in hindsight. Right.
Don't you love when that happens when you like learn something new and you're like, oh yeah, well now I understand.
Non-recursive. That's why I like the recording. Like, wow, I wish I knew this.
Yeah, right. I mean, that's the trick is like, there's just a lot of information at once. And when you go back to your homeworks at the end of the semester, like homeworks 1 and 2, you're gonna be like, oh my gosh, it was so easy, right?
I feel that way.
Yeah, why did I make that mistake?
I know, it's tough, it's tough. I mean, yeah.
First time in a long time I've had a math class where I felt compelled to show my work in case I actually did get something even wrong.
Yeah.
I was like, I know I missed the negative sign.
Oh my God, that question, I know. I had a different path model and I found that new one because I didn't like, the old one was like about fathers and sons and education and income and stuff. And I was like, I gotta change this example. But yeah, I worked through that and I was like, I did it like 3 times just to make sure. And then I made Jocelyn do it too. Like, I just want to make sure I didn't make any stupid math mistakes. It is tedious. The good news is you're not going to actually have to do that normally. But I think it's good to go through the process so you understand sort of how it works. But I mean, the good news is, normally Mplus is going to be doing it. Mplus is going to tell us what the model applied correlations are. We're not actually going to have to do it by hand. Yeah,
I understand that the recording's still on.
that is true. Recording is still on. I should turn there. Now you have to remind me to turn it back on. And let's resume.
Were they?
All right, let's go ahead and get started. So I don't know how many of you have had classes in this room before. Raise your hand if you've been in this room for classes before. Okay, most people, but not everybody. So we're going to use the courses folder is where I'm going to put all of the input files and things that we need to run our examples. So let me show you how that works if you don't already know. And if you are on a laptop, then you're going to have to get this stuff on your laptop yourself. Everything that I put in the courses folder is also in the Husky CT, the Blackboard site, so you can do that, but it's just a little more cumbersome. But you know, if you have like well, it's not that much more cumbersome. You just have to download it from Husky CT, right? Okay, so in the courses you'll find somewhere on your desktop a little folder, right? A little shortcut to a folder called the courses folder. And if you double click on that, you'll actually see a whole slew of folders, and we're 6615. So if you click on that folder, you'll see some stuff. This is all the old from 2020. I don't know. I probably should have taken it down, but I just left it there just in case. And then there's a week 3 folder. The easiest thing to do, because we can't all be running from the server at once, the easiest thing to do is just to copy that folder. I've already done this actually, and then just paste it onto the desktop. And then you can just work from the desktop. And these computers are set up such that I think at like 11 or 12 every night, it just wipes, not on the instructor one, but on all the other ones, it wipes everything off the desktop every night. So you can just put the week 3 folder on your desktop, and we'll just work from there, and then it'll just disappear. So anybody have any questions about any of that? Does that make sense? Okay.
Yeah, it needs an admin to allow the network sharing.
To allow the network sharing. I don't know what you even. No, I mean, did you click into the courses folder?
I mean, it
Yeah,
doesn't even open the
Here.
Well, yeah, no, don't do that. Just go to the courses, the shortcut here. Courses
got it,
folder.
got it.
Click on there, right? And then when you click on the courses folder shortcut, then you'll see it, and then just copy week 3 and paste it onto the desktop. Yeah, just go right to the shortcut and click on that, because network is actually something different. Okay? So does everybody have week 3 there? Yeah? Okay. So now, if we're gonna use Mplus, yay! So there should, I think, on all of your computers be a little shortcut to Mplus8. Yeah. So if you double click on that, Mplus will come up. Yay! And this is, it doesn't look too fancy, but this is Mplus. Also, if you don't have a shortcut, you can always just go, and you should find it under M for Mplus. So the other way you can get there is just to go to, if you do that, you want the one that says Mplus editor with the big blue M on it. Okay. So Mplus, how many people have used Mplus before, by the way? Anybody? Okay, not very many people, just you. Okay. So Mplus, I mean, there is actually sort of there is some capacity to draw diagrams, and it will draw diagrams out, but the diagrammer is not the best in terms of setting up your models. At least I don't think so. We're definitely going to set everything up in terms of a syntax. And actually, if you go into the one thing I didn't print out, but is up on Blackboard, if you go into, I think it's in here, PDF. Oh, maybe I didn't put it. Maybe I only put it on the. Oh wait, I can go back to. Plus, I guess I didn't put the little Mplus Word document in here. Well, that's unfortunate. But there is a Word document that sort of explains some of the basics of Mplus. But Mplus is a it's on Husky CT. I know it's on Husky CT, and actually I can find it. I know it'll be in here. This is why I leave from 2020. let me go back here. Go out. If I go to from 2020, there you go, 6615. I'm pretty sure it'll be here, probably in week 2. Yeah, okay, I was wrong about that. Okay, that's interesting. Oh well, whatever. So it's labeled Mplus notes. I don't need the notes, but you will need the notes later. So Mplus is a syntax-based program. There are a whole series of commands in Mplus. And so actually, the commands all get followed by like a colon, and they generally sort of appear in a particular order. I don't know that the order actually really matters all that much. The first command is actually like title, right? So the title command really doesn't do anything. We can just put a title for our model in here. So let's just call this, I'm just going to call this first Mplus model. Okay, so that's the title. Now the next thing that's going to be really important is the data command. And the data command is going to be where you tell Mplus to, yes. Oh, bigger, yeah, let me make the font bigger. Good point, thank you. Let's see if I can just remember how to do this. I've done it before. No, I don't think that's it. I think it's change font. Here we go. Right? So I can go choose font. Like that? Is that big enough? Yeah. Okay. Sure. So here we go. So title, first Mplus model. Great. Oh, it didn't change for everything though. Look at that. I might be wrong. Hold on. Let me try this again. Where was I? Change font. Choose font. Okay. Okay, now it looks like it's better. Okay, so the next command is going to be the data command. And this is where we're going to tell it where our data are. And the data for Mplus, this is one of the sort of the wonkiest things about Mplus actually, is that you need to read in either a CSV file or a .dat file. So it's either going to be just sort of like a basic flat like text file that's got a .dat extension. And that's generally what I'm probably going to use for most of the examples. Or it can be just sort of a flat data file with a .csv extension. But you can't read in like, you know, SAS or Stata or SPSS files. So if if you're working in R, it's not like any big deal because you probably have a CSV file already, right? But if you're working in like some other package, then you're going to need to save out into a CSV or a .dat. We can also use correlations or covariances as our input. And in that case, we're actually going to have to tell Mplus that we're using covariances or correlations, which I think, you know, I have the directions for how to do that on your homework, and I think I've got it in the slides here too. So you're just going to tell it that the type of data is a correlation file or a covariance file. But here we're actually using raw data. So let's see. Let's set up our first model, and our first model uses. This is not my first model, but that doesn't matter. We're using the same data file. So we're just going to say data file is, oops, I usually like this skip. What? Yeah, example 1 is the one that we're gonna set up. So when you are telling it what the data file is, you're always going to say file is. I mean, actually syntax based, but the syntax is very intuitive, I find it. So data file is, and then we're going to tell it the name of the file. So I think our file name is, that's where I need to check things, SAS R underscore 2013 .dat. Oops, not DAQT, .dat. And then every line is going to end with a semicolon. Okay. Now I didn't actually end the title line with a semicolon. It turns out actually, and this is just like a really nitpicky detail, but it turns out If you forget the semicolon at the last line before the next command, and you see how the commands are showing up in blue, that's fine because it'll know that you're done because you're moving on to another command. But otherwise, you absolutely have to have the semicolon. Otherwise, it's just going to read the next line as if it's part of the same command. So it'll work. I mean, for title, I could put a semicolon. I also don't need to. But here, if I'm going to say anything else about data, I'm definitely going to want a semicolon. So it's just a good habit to put semicolons at the end of every line. Now, I don't.
Sorry.
Yeah.
The phrase fine is, it doesn't matter that it's in uppercase here or.
Oh yeah, no, Mplus is not case sensitive. So yay for those of us who are bad at remembering case sensitive stuff. So you don't have to worry about whether it's uppercase or lowercase. So you can use either without worrying about it. Now, one thing that you do want to do here is that is going to be important is if I don't want to have to give the full path name of where the heck my data is, because that's like one choice, right? I could say file is, or I could give the whole C path, like where is it located on my computer. If I don't want to do that, which I generally don't because I'm kind of lazy, what you can do is just make sure to save your input file in the same folder as the data. So as long as your data is in the same folder as the input file, then this will work. File is sasr_2013.dat. But if your data file is not in the same folder as your input file, then you are, just like with most other computer programs, you are going to actually have to tell it what the path is to go find the data. So for this class, I'm always just going to save the input files and the data files in the same folder so that I can do this, which is really useful because your path and my path wouldn't be the same anyway, but just something to remember. So actually at this point, I should probably say like save as, and I'm going to want to go to my desktop, week 3, example 1 path model, and I'm just going to call this in class because I already have actually one that has the full input in class. I don't know, example 1, it doesn't really matter. Save. Okay, so now I know that I've saved it in the same folder, in the same directory as my data. Okay, so that's it. So that's all I have to say about data. If it's raw data, this is it. This is all I have to say. Then the next thing that I'm going to do is I'm going to need to tell it about the variables. Okay, so I'm going to go variable. And again, you see it turns blue. So variable is a major command. And this is where I'm going to tell it, the first thing I need to tell it are the names. So to do that, I'm going to say names are, oh, well, I didn't tell you what your data file should look like. Again, you don't have to worry about this for your homework because you're getting all the files from me. But in Mplus, your data file needs to just be numbers, not any words. And that includes like so even the first line of the file should not have the variable names in it. So you're just going to have the data, but not any variable names. So the only way that Mplus knows what your variable names are is when you tell it right here. So it's going to be really important when you do this to enter the names in the order in which they are in your data file and to list all, you should have a variable name for every column in your data file, right? And it should be in the same order as your data file. And you can name it anything you want. It doesn't have, because you're not bringing in the variable names from anywhere else, you can give it any name you want. And like, this can seem really tedious, right? Like, what if you have 1,000 variables? Well, you have 1,000 variables. Maybe you don't want to bring them all into Mplus, right? Maybe you only want to bring the ones you're analyzing in. So that's one answer. Another thing you can do, which is cool, but also can get you in trouble, is I could be like, hey, names are variables 1 to 1,000, which is great. That'll work. It's going to name your variables 1 to 1,000. The problem comes in, it's like, now you've got to know that you're using variables 253 and variable 896, right? So, I mean, there are easy ways to enter in your variable names, but you also want to be a little bit thoughtful so you don't get yourself in trouble later. Now, and again, you need to name, there needs to be a name for every column. It's really important because, that's going to sort of signal to Mplus how many variables are in the data file. So here we have names are, we don't have 1,000 and we're not doing this. So I'm going to name them GPA homework, because again, this is that same example. GPA, homework, academic self-perceptions, ASP, goal evaluation is GV, and I'm going to call this MOT SR for motivation self-regulation. So in our data file, if we were to look into that .dat file, we would see that there are only 5 columns for the 5 variables. Now, if you're not using all of the variables, then you're going to want to use this use variables command. In this case, we're using the 5 variables that are in our data file. So I don't think I have it in the input file that I gave you, and I don't really need it, but for completeness, I'm just going to talk about this for a second. So
That's supposed to be one word.
yeah, it is actually supposed to be one word. It's a command. So use variables are is just signifying what the variables I'm using in my model are. So if you have like 20 variables in your data file, but you're only using 10 in your model, then you would put names are and put all 20 variables, and then the 10 that you're actually going to be using in your model, you put in the use variables command. And then that tells it, yeah, okay, I'm not using those other ones, right? And you definitely, this is really important. If you've got variables that you're not using in your model, you definitely do not want, you need to tell Mplus which variables you're using. Otherwise, it's actually going to stick all of those variables in the model and assume they're just uncorrelated with all the variables in your model, and your fit will be atrocious. So you definitely need to do this.
So do you recommend just saving the original data set as the variables you're going to be using for a model?
Saving the original data set as the variables I'm going to be using for the model. Yeah, I mean, I tend to create because I'm creating a dot, well, again, it depends, I suppose, on what package you're using to begin with. I mean, I tend to save a smaller data file, even if no matter what package I'm using, I tend to create a smaller data file that I'm going to use for my analyses. Because again, I often have data files that literally have 1,000+ variables, but a lot of them are very, I have this master data file. It's got all the sort of variables, and then I've done a lot of screening and cleaning, and then I've got the sort of the variables I want to use. So I'm almost always creating a smaller data file, but it's really up to you. I mean, you can have a bigger or a smaller data file, but I think it's easier to work with a smaller data file. And you can have some variables that you might not use right now, but you might use later. That's fine, but you probably don't want to bring in 1,000 variables. I think it just gets cumbersome if you just create a sub, like a sub whatever group of variables that you're using. Okay, so that's it. Now, if again, we don't need this today, but if you have any missing data, you're really going to want to code that. The easiest thing to do, there are options, but definitely the easiest thing to do in Mplus is to have a numeric value code for missing data. So, and you want to make sure that you use a numeric value. You can have multiple numeric values, but whatever you do, you want to make sure you use a numeric value that isn't going to actually be any of your values for your data, right? So, I could say something like missing are all. That would mean all variables are going to use the same, like, all variables have missing data. And then I could say like -999, let's say. And that would tell it that, all variables have some missing data, and my missing value code is -999. And again, if you have a missing value code and you forget to say this line, it's going to be bad, because every -999 is going to be treated as if it's like real data. You should be able to pick up on the wonkiness of that when you get your first output file and the beans look really strange, etc. But that's important. Yeah.
For the parentheses, are you doing that because it's a numeric value or because there's an extra?
I'm doing it because that's the code for Mplus. I mean, like this missing are all is the command, and then in parentheses you put whatever the missing value codes are, and it doesn't matter whether it's positive or negative. So I could actually have this, by the way. So all here just means all my variables, and I could have multiple missing value codes. So it could be like this, let's say. I'm just making stuff up now, right? I could have 4 missing value codes, and those would all go in the parentheses, positive or negative, whatever. Again, I think here we don't have any missing data, so we don't need this. Oh, well, that's a good point. If you have a line of code in Mplus that you don't need in this run, and this is going to be a nice little trick for you, you can just put an exclamation point in front of it, and that, see how it turned green? That means Mplus is not going to read that code. So this is really handy for, sometimes you're running models and you like, you know, you want to mess, like, whatever, you want to mess with something and then not mess with it, like the deleted paths, right? You might have you can sort of have them in and out just by having a line that has the exclamation point, and then you could have them go in and out. Also, it's really handy for making comments for yourself. Like you want to remind yourself, oh yeah, this line means missing data. This line means whatever, whatever. So that's kind of cool. So we don't actually need that line, so I've just commented it out. Yes, question.
So is that you telling Mplus to assign those?
No,
Or
this is
is that
me
you
telling
telling-
Mplus that when you look in these data, you're going to find some negative 999s, some negative 998s, and those values mean that those.
you've already put on the
Yeah, they're already in there. So this is important. You've got to deal with your missing data before you come into Mplus. And again, I mean, there are other ways to deal with it, but the easiest, so there are other options, but the easiest, most foolproof way is to actually give it a numeric value and then to tell it that the missing are that numeric value. Yeah.
I'm saying we can put these like comment lines on the same line as other codes.
You can, but you can. The only trick there is that Mplus actually only, you'll see this as a warning, by the way. I forget exactly how many characters it is, but Mplus I think will only read about something like 80 or 90 characters, and then after that the line will get truncated. So it's, you know, it's a great package in some ways, but it's very old school in other ways, you know. So like you want your variable names generally to be 8 characters or less, because it will truncate the variable names after 8 characters, and it will also truncate. It's usually about here that it will stop reading the line. And so if you have, like for example, if you had 50 variables, you couldn't just list them all on one line. You'd need to like create a line break, but you just wouldn't put a semicolon there, and it's going to read it as all one line, because the semicolons are what are telling Mplus that you're starting a new line of code. But if you try to make it too long, it's just going to stop reading at that point. Now, back to your point, if it's a comment, like who cares, right? In that case, it doesn't really matter, but it's just, you know, it will A, give you that warning when you do it, and B, might not actually print it all out on the output. So you just want to be, for comments, it's not such a big deal, but certainly for code, you want to be cognizant that you don't want your lines to get too much longer than this. I mean, they could get a little longer, but you don't want them, you know, if you go all the way to this edge, it's not going to read over there, right? And then it's really going to be problematic, because if this is one line and there's a semicolon, it doesn't understand that that's the end of the line. And so whatever comes next, it's going to assume it's just a continuation of that line, and all kinds of weird things will happen. But, you know, you'll get used to this. Is there anything else I want to say about the variable? I think these are the, I mean, again, as we go through the semester, you'll learn more and more options, but these are kind of the biggies, like knowing names are, use variables, and missing are like 3 that you generally need all the time in your own work, almost no matter what, right? Okay, so now the next thing, the next statement I'm going to use is the model statement. And this is where all the, and I just skipped a line. I don't know why. You don't need to. I think I just did it for effect. But like having spaces between is probably not a great idea, because it's going to print out that way and it'll take more paper, but whatever. So the next statement is the model statement. And this is like the heart of where you tell Mplus what the model looks like. You know, what is the model that you're fitting? So all this other stuff is, you know, just sort of more, I don't know, housekeeping, if you will. There is actually, I guess I should mention that. Maybe that's why I skipped a line. There is another command that we will eventually probably do something with called the analysis command that I always think of, like I think of these in an order, although I don't know that it really matters what order the commands are in, but this is the order in which they're presented in the user's guide, so the order in which I think of them. And the analysis command is where you can give all kinds of options about the analysis. So like what estimation technique you're going to use. That's probably the most common thing. You can up the number of iterations. You could change the convergence criteria. There are lots of things that you can do in the analysis command to, like, you know, it's not all about estimation, but a vast majority, a lot of the commands really sort of deal with kind of messing with the way that you're estimating the model. So again, we'll come back and talk about some things in the analysis command later, but we don't need anything for that here. And it's fine for me to just leave it blank like that. That just means I'm using all the defaults, but I could also leave it out because I'm not saying anything. But model is really where the action is. Okay, so the first thing is, there are a couple confusing things about Mplus at first, but you'll get used to them. The first thing is that it really, and maybe this won't be confusing to you, it depends on how you were taught regression. But when you learned about regression, did people talk about the dependent variable being regressed on the independent variable? Is that the sort of the verbiage? Great, and you'll have no problem with this, because that is the command, not regressed on, but just on. So if I say y on x, that means y is regressed on x. And the thing to remember is it's the, like, the outcome variable, right? That's going to be on. I could draw it in case any. That's a good idea. Okay. So if I say y on x, right? That, maybe I won't use an arrow just tonight. That means actually that x predicts y, right? That y is regressed on x. And on is the command for paths. So we're always going to have the outcome variable, and it follows like a regression equation kind of thinking, right? In a regression equation, we have y is regressed on, we have these x variables, blah, 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 right? So it's that kind of logic, y on x. So outcome variable, and we can have more than one independent variable. We could have this, we could have y on x1. Well, it's not going to be subscripted. X1 and x2, right? That's fine. Y on, and so that's saying that x1 and x2 both predict y. I could also, by the way, it's not going to matter. There's a lot of flexibility. I mean, there are lots of rules, but there's lots of flexibility. I could say this. Y on x1, x2, semicolon, y on x3. Now, that's a sort of a very flower, like it's unnecessarily long in the sense that I could have just put x3 up here, but it doesn't matter, right? Like it's going to read all these lines and put the model together. And the reason that this can be useful again is, you know, maybe this is your deleted path. Right? Maybe these are your conceptual paths, and this maybe is your conceptually omitted path. So maybe you want to put it on a separate line because, you know, if it turns out you don't need it, then you could just comment it out. See what I mean? So sometimes using as a longer strategy ends up saving you time in the end. Point is, it doesn't matter. You can have you can accomplish the same thing in multiple lines or just one line often. Yeah.
And multiple lines? Since we have multiple endogenous?
Oh yeah, totally. Yeah, yeah. So we're going to specify, and that's a good point, for every endogenous variable, we're going to have at least one line of code, right? And again, I guess, you know, I guess you can have multiple y's on one line. I never do that, though. I always have a separate line for every one of my endogenous variables, but I think you could say like y1, y2 on x1, x2. That will work. You'll see I never do that, but it should work. Okay. So for this model, you have the conceptual drawing, right? And by the way, when we're putting lines in the model code, we got to make sure we get the whole model specified, but we don't have to worry about the order. So if you want to start with GPA and work your way up, you know, if you want to start up here and work your way down, it doesn't matter. The statements will be in different orders, but they'll be the same statements. And it doesn't really matter what the order is, because it's just gonna sort of read it all. It's a model that's gonna be simultaneously estimated, so the order doesn't matter. So I think in the code, I started with GPA and worked my way up. To me, that kind of made sense because I'm doing GPA on, right? So I'm just kind of working up. Okay. So for the model statement here, then it's GPA is regressed on, right? And I'm going to look and I see, you know, if you look at your picture, you can see GPA is regressed on academic self-perceptions, homework, and goal evaluation, right? Got to make sure you type these exactly the same way. Yep. Okay, good. And then I also have that conceptually omitted path for GPA, which is GPA on motivation self-regulation. Remember? So I'm just, again, you don't have to make this a separate line, but I'm gonna make it a separate line just to make my life easier later on. So I've got GPA is regressed on academic self-perception, homework, and goal evaluation. And here I could say in comments, these are my conceptual paths, right? And GPA on motivation self-regulation, this is one of my, you know, conceptually omitted paths. Okay? And you can see that this is kind of important too. Notice that I put the semicolon before the comment because everything after the comment is going to be green. So just make sure you put your semicolon first, and then you can comment on the same line if you want to afterwards. And you won't have you don't need a semicolon there because it's not being read anyway. Okay. So now the next line is going to be, now I got to think about homework, right? So homework is regressed on, let's see, motivation, self-regulation. And that's it, right? I mean, again, of the conceptual model, but for the just identified model, homework is also going to be regressed on academic self-perceptions and goal evaluation. Everybody follow? Does this make sense? Okay, great. And then motivation self-regulation is regressed on academic self-perceptions and goal evaluation, right? And then finally, I'm going to put this in academic self-perceptions with goal evaluation. That's that curved arrow, right? So that's the correlation between exogenous variables. Technically, you don't, I mean, technically by default, Mplus is going to correlate all of your exogenous variables by default, just the same way that a multiple regression package would correlate all of your independent variables by default. So technically, we don't actually need that line, but it's a good opportunity for me to introduce our next command, which is with. So on is regressed on, so that's a path, right? With just means that these two variables covary with each other. No, not now. So academic perceptions with goal evaluation just means academic perceptions is correlated with goal evaluation. Now, if I wanted to correlate two endogenous variables, well, let me say this. Mplus does not make it this, I mean, it does, of course, understand the distinction between endogenous and exogenous variables. But in Mplus speak, if a variable is endogenous, then it, you don't have to make a distinction between like a disturbance and the endogenous variable, for example. So if I just put, let me say this in an easier way, I'll show you. If I say just a variable like this, again, I don't have to do this because it's going to happen by default. But if I say ASP, GV, and then semicolon, that's actually saying the variance of academic self-perception, the variance of goal evaluation. So like if you just put a variable and it doesn't have like an on or with, you just have the name of the variable, that means the variance of the variable. which again, these are going to get estimated by default, so I don't necessarily have to say it right now, but this becomes important later on. So I say academic self-perceptions and goal evaluation, that means estimate the variances of those two things. Now, on the other hand, if I put, and I'm putting these on separate lines, but they don't have to be, homework, MOTE SR, and GPA, okay, those are all endogenous variables, and so we're not actually estimating a variance for any of those variables. We're estimating disturbance variances. So when Mplus refers to something like, when it refers to homework, right, like the variance of homework, you have to know that the variance of homework isn't really the total variance of homework, because homework's an endogenous variable. It's the disturbance variance of homework. And I think this is sometimes confusing at first. It ends up being really nice later on once you kind of get used to it. So basically, if you refer to a variable, just like refer to it, if it's an exogenous variable and you just refer to it on a line, that says the variance of that variable. If you refer to it just like that and it's an endogenous variable, you're actually referring to the disturbance of that variable. Does that make sense? Or the residual of that variable. If it's an indicator in a CFA model, it's actually going to be referring to the measurement error of that variable. So if it's an endogenous variable, you're really talking about the unexplained part. If it's an exogenous variable, you're talking about the whole thing. And there's nothing here that's going to indicate that. You just have to know that's the way Mplus is thinking about it. So I think at first that seems confusing to people, but like I said, once you get used to it, it ends up being really nice. Yeah.
Here, what's in parentheses, it's just a comment.
Oh yeah, sorry. Really good point. I forgot to put, there we go. It is just a comment. I needed to do that.
I also have a question when you are
Yeah,
ready.
Hannah, what's up?
So I think I'm looking at the right thing, the conceptual model where like you've drawn it out and you've like labeled it in pencil, it looks like. So my question is why, I guess I just want to make sure that the line that you have that says homework on ASP/GV, that's also omitted, right?
Yeah, I didn't, you're right, it is. I should have, I didn't comment it, but you're right. I'll do that right now. This is, right, these are my other conceptually omitted paths.
Yeah, I just wanted to make sure I was following, that I wasn't missing anything.
You're totally right. You're totally right. Yes, Katie.
So with that line, why did you do the two paths like together instead of writing them separately?
Because they were both conceptually omitted. So again, they could all,
Make any difference?
no, I could have written them separately.
Okay.
It doesn't matter. I could have said homework on ASP, semicolon, homework on GV, semicolon, or I could have said homework on MOTE SR, ASP and GV, semicolon. It really doesn't matter. So that's nice. You have options. So your code might look slightly different from somebody else's code because of the way you sort of format it that way, but it's not going to matter. Yeah.
I don't understand how the Mplus identify or how you tell them when it's a consensual path or when it's an omitted path.
It doesn't know. It doesn't care. It doesn't need to know. You need to know, but it doesn't need to know. Right? Because remember, step one is I fit the model that includes the just identified paths. So this is just my step one syntax. And then I'm going to look at the output and I'm going to decide how I move on to step two. Right? So like Mplus doesn't know that which path, it only knows you're fitting those paths. I've put comments there to remind myself that those are the conceptually omitted paths. So I remember those are the only ones I'm going to look at in this run. But Mplus doesn't know, and Mplus doesn't care. It's just a path. It's just a computer program, right?
So
yeah.
We could have just put all of the paths on one line for each variable.
Totally. For every variable, you could have just had homework and then had all of the different predictor variables for homework. I just did it this way because I just thought it might be easier for me if the conceptually omitted paths are on a different line, because then for the second run, I could just comment them out if I don't need them. So that was just my thinking, but it really doesn't matter. And it's nice, there are a lot of options here. But what's really important is the on, right? So whatever's before the on is going to be the outcome variable, whatever's after the on is the predictor variable, and just think of it as regressed on. And when you have a with, that just, and obviously order doesn't matter with, that's just a correlation. Or covariance. Technically it's a covariance, but again, standardized will be a correlation. Yes.
I love it. You can take notes in this. Do the notes print out? Do the notes saved?
Yeah, as long as you don't go past that 80 or 90 characters, you'll see the notes printed
Okay.
out. Yeah, absolutely, which is nice actually. And you can have notes on separate, like I have here. You can have notes on separate lines. They don't have to necessarily be just on the same line either. So you can write yourself a little paragraph if you want, and just comment it out. Yes.
Is there any, like, I know it's the exclamation point for one line. Is there a way to like comment out several lines at once?
An exclamation point at the beginning of each line.
Yeah, so I can't like do another command and keep going on line.
No, because it, when it gets to that 80 characters, it starts with a new line. So no, you would have to put an exclamation point at the beginning of each line. It's not going to remember, just like it doesn't, it just kind of stops there and then it goes to the next line. So yeah, so you can have multiple lines, you just need multiple exclamation points. Okay. Other questions before? So we've got our model statement, and then this is it. We've actually, if you look at your, again, this is, Mplus does a lot of things by default that are kind of nice. So, I've actually specified here that I've specified all my variances, the exogenous and the endogenous disturbance variances, and I specified the correlation between the two exogenous variables, but technically you don't really even need to do that. I think it's good as we get started to kind of remind ourselves about that. But if you look at our model, and actually we should not look at our conceptual model, we should look at our just identified model, right? You'll see, if you kind of look back and forth, you'll see that this just identified model actually matches the code here. Yeah, so that's good. We got everything in there. And so now the last thing is output. So the output command is what you use to specify particular types of output. So by default, you're going to get unstandardized parameter estimates, but if you want standardized estimates, which you generally do, you're going to need to say that. So you could say standardized, and that will give you, I don't think, what did I say here? Yeah, that will give you 3 different kinds of standardized parameter estimates. You'll get what are called STDYX, which is kind of the most common, that's the kind of standardized parameter estimate you're generally going to want. If you're working with continuous variables, STDYX is what you want. The other 2 standardized variables, they come into play more when you have categorical variables in your model. And there are 2 different ways of standardizing, taking into account the categorical variables. So the completely standardized model is STDYX. And I'm going to type STDYX that's going to give me those standardized parameter estimates. Again, if you can't remember that, you can type standardized, but then you're going to get 3 times as much output. So, and then let's see, what else do I want to do? I think I'll put in mod. I talked really briefly about them, and I had it here. I'll put in modification indices, and I'll just put mod indices 4. There we go. And I could put in residuals. I didn't have that before, but let's see, Now I have a problem. I always forget if it's residual or residuals.
Residual.
With an S.
No,
Without the S. Okay, see? I was gonna say, I can't tell you how many times I run something and I'm like, oh yeah, no S. Okay. So we put in residual, and that will actually give us our residuals. Yeah.
Why 4 for mod?
Oh, that's a great question, Katie. Why mod indices 4? Well, I could put any number in there, but it means mod indices 4 means give me all of the potential modifications that would make the chi-square drop by at least 4 points. So if I added this parameter, chi-square would go down by at least 4 points. Why do you think I used 4? Any ideas? Yeah, like 3.84, but I'm rounding up to 4, right? So I'm kind of saying like, hey, if this modification doesn't drop the chi-square by at least 4 points, I don't care, because it wouldn't be statistically significant. I mean, again, technically 4 is bigger than 3.84, but that's close enough for me. So that's why I use mod indices 4. I don't always use mod indices 4, but that's actually what I had on your paper here. All right. So I think we've got everything here. Oh, SAMStat. Yes, thank you. I should definitely put in SAMStat. So SAMStat just gives you sample statistics. So it's always, I didn't have that on here, but probably because I wanted the output to be shorter. But in reality, you pretty much always want those sample statistics. You'll get some stuff otherwise, but SAMStat is really useful. So SAMStat, so generally STDYX, SAMStat, and residual, not necessarily modification indices, but those are 3 that you're generally going to want to put in your model.
So SAMStat is just the descriptive statistics of the sample, like.
Yeah, it's descriptive statistics, although you'll actually get like they're not necessarily always exactly the same as what you would get from SPSS. If you have no missing data, they will be. But if you have missing data, then it's going to be like your maximum likelihood estimated sample statistics, you know? So they'll be very similar, but maybe not exactly identical. Does that make sense? Yeah. Okay. Yes.
Can you repeat again the 4 is to down, like if the factor go down to 4, what happens?
Oh yeah. So the reason that I put modification indices 4, mod indices 4 here is because I don't, well, first, I haven't talked much about mod indices, so I don't want to get too much on a tangent, but generally speaking, I would never want, the mod indices is just going to give me, what parameters could you add? It's not going to give me anything here because the chi-square is going to be 0, right? So we're not going to get any modification indices right now because it's a just identified model. But like in general, mod indices 4 says, like how much would the chi-square go down if you added this parameter to your model? And remember I said, you know, we tend to favor parsimonious models. So if the chi-square is basically unchanged, we wouldn't want to add that parameter. So the logic here is I wouldn't want to add a parameter that doesn't decrease the chi-square by at least around 4 points. I mean, technically I could put 3.84 in there if I really wanted to be. You could do that actually. It's not like it has to be an integer. I could say chi-square equals 3.84, right? And then it's, again, it's going to give me nothing because we're going to have a just identified model, but that's going to give me all of the potential parameter, like all of the potential parameters that I could add. How much would the chi-square decrease if I were to add that parameter to the model? Okay, so that's it. You ready to run it? So let's save it again. And let's go ahead and hit run. Hey, and it ran. That was quick, right? Now I think I have to make this font bigger again, right?
Oh, do you all have the data?
What?
No, because it didn't run. I didn't run. So I'm thinking it's the data. They have it saved in the same.
Oh yeah, make sure that you save it in the same folder, in the same subfolder as your data. You need to save this input file in the same folder as your data. And by the way, there is one annoying, I think annoying. There is one annoying thing about Mplus. So the one annoying thing about Mplus is that for every model, you actually need a new input file. You can't just stack model after model after model in one input file, which is annoying. So that's why we're going to have multiple input files you always see when we're running models. So who didn't get output? Oh, wow, a lot of people. Let's see. What happened?
I think I have that myself.
Oh, no. Okay. Syntax. Okay, so go down to unknown data option 5. Oh, yeah, all right. It's not file. It's file. I do it back to your- Yes, you know, right, file.
Oh, it's too late.
Yeah. Mod. Oh, yeah, you got an I. There you go. Mod.
Oh, it pops you out, okay.
Yeah, you're still. There you go. That's right. Yeah, often that's all.
So like more.
Yeah, yeah. Okay, how about my visual? Sure. And luckily you chose it, right? Yeah. Which is really nice, yeah. Oh, sure. Oh, I see. Okay. Okay. Good news is, scroll down. It gives you some, okay. Morning. So those are just all about. Nice characters. That's what you have.
Okay.
Wait a minute. Error, input reading ended with mismatched block comments using blank and blank. Check your input and verify that.
Where is your?
Yeah, there. Let's see, yeah.
The-
Oh, I did.
this-
That's probably that, but I mean, it's fine. No, I don't think I own that. I think it's-
And then
Like,
say,
I'm still saying, you just see like fingers out there. I'll tell you later. I think there's probably something like that. Yes. Yes. Okay. Yeah. Well, there we go.
It's easier.
Because it's.
Right.
Yeah.
Yeah, that's right. Because I wanna- because I wanna-
I know, wasn't it? Oh, I didn't put it. What is a mismatched block comment?
Yes.
So I think that's right. That's what I said earlier.
You got it? Yeah.
But that's okay. Do you see what I mean? I think it's the same thing. Then if it starts with that, then it's gonna end with that, and that's what I'm doing. And if it goes like EPSY and every line, it starts with this. Do you see what I mean? Okay, Jason, you close. So I think that, I didn't know that, but I think that actually explanation of star.
yes, it's a lot of.
Yeah, but then you have to end it with star. See what you use it?
Yeah.
I usually try to remote select. And I got one that inputting the address and the
Oh, yeah.
All the stars, or make sure your exclamation point star stars. Okay, how about everybody else? Anybody else? Yeah. Resource, time block. Well, I don't know how you try to connect to, you're not gonna be able to get to your system.
No, I was just trying to get to the desktop.
Ooh, yeah, that is probably a good 40 question. Yeah. That's really weird why that happened.
Right, so I
Oh, okay. Yeah, that's good. Yeah, probably. And we should talk to Cory after class. Okay, did everybody?
Betsy, I
else
have
say something? Yes?
Betsy, I have a couple questions.
Yes, Hannah.
So for one question is, can we save work on these, like on the desktop?
I just tried and it wouldn't.
Okay, because that's a little bit of a problem if you're trying to do it remotely, because if you try and access, like I got disconnected because I tried to sign in to my like Yukon account like on Blackboard to download the materials because I didn't realize they were already in a folder. So I guess my question is like, how do we handle that?
What do you mean by you can't save on the desktop?
So if you are, working on something on Mplus and you want to save your work in the file, can you save it there and it won't get like wiped after
Yeah.
a day or something?
Oh, well, it will get wiped at the end of the day. But you should be able to save on the desktop. You should be able to save on the desktop right now. Like, it's not like you can't save, it's not like you wouldn't be able to save your output on the desktop right now.
But how would we access this like tomorrow if we wanted to?
Oh, yeah. So if you're remoting in, you're gonna need to like actually, once you run the stuff, you're gonna need to like send it to yourself or save it on your hard, like copy and paste it on your own hard drive or whatever.
But only do it via email, because if you try to log in to like Blackboard or something, it ends your remote thing, and now I haven't been able to
I
get
did
back
not
in.
know that signing into Blackboard ends your remote thing, but I do think emailing it to yourself is probably the easiest way to do it. So like if you're remoting, and that's going to be true here too, like if because as I said, everything's going to get wiped at the end of the day. So everything that we've done right now, even though you're sitting in class, if you want this, you should email it to yourself at the end of class so that you have what you did, because it's not going to be here. It's not going to be here tomorrow. Yeah.
Would you just copy and paste it out into something else?
You could do that too. You can copy and paste it out into something else. You can email yourself the output file. You'll be able to open up the output file without any problem, even if you don't have Mplus, because it's just a text file.
Oh.
The input file, not necessarily, but the output file you should be able to open up in any text editor. Actually, the input file you can open up in the text editor too. You just can't run it. Yeah.
The other,
Oh, sorry. Okay, Hannah. Yeah, and then Amanda.
okay, the other question I have is like, I can't find any clear like point person for what to do when we are disconnected from remote access and can't get back in. Is that just anyone at IT, or do we have a specific person?
That's a really good question. Well, Corey is our point person in the School of Ed, but he interfaces with the IT people. So it's I don't have a direct person at IT. So you can email, he's gonna hate me for this, but you can email Corey Joyce, which is CORY.JOYCE@UConn.edu. But the reality is that if it's something that's real, IT set up the system, so he's probably not going to be able to, he may have to like say, okay, well, I'll let IT, he may not be able to immediately solve it himself. He may have, yeah, well, he's a little overwhelmed because there used to be somebody else. He's got two jobs. That it used to be Jameson who did all this, and Jameson was great, and Corey is great too. But unfortunately, they didn't actually replace Jameson, so Corey's a little overworked right now, which is the other reason I'm a little scared to say is email Corey with all of your problems. But maybe Jocelyn, maybe we can find somebody at IT who'll be our point person. I haven't found IT to be incredibly helpful, to be quite honest. So
If this bit was time out and then eventually you can get back in, Hannah, but I don't know about it in the meantime.
yeah, that's kind of a pain. And then, but also just FYI, so you can always come directly to the lab when you're on campus, right? So you may find the remote, we had the remote thing like last time, fall of 2020. I'll say it took a couple weeks to get the bugs out. It did. Like the first couple weeks were kind of annoying. But then by about 3 weeks in, I think everything, the kinks were out and it worked really well for the rest of the semester. But if you really get stuck, you can come in here and use the lab. I know it's locked right now, but Corey's setting it so that it'll be open from 8 to 5, Monday to Friday. And as long as you get in before 5, you can stay as long as you want. For those people who are MEAG students, you can actually get your key card, so your ID, so that you can get in anytime. But if you're outside the School of Ed, I don't think that I asked once before and they kind of said no, but I can ask again. I don't think that they will do key cards for people who are outside the School of Ed to get in, but you can get in Mondays through Fridays, 9 to 5, and then you can stay as long as you want. So if you really get stuck, you can come in. There is no like student version of Mplus, so it's not like That's not an option, like it is with some other programs. Yes, Amanda, question.
One other solution for saving files is OneDrive. So like if you're logged in anytime with your NetID, you have access to OneDrive, and it's like a really big file. Like one.
That's a good point. OneDrive is a good option, probably.
Like right now, if you just go to OneDrive, you'll see your own folder, and then you can get that on a personal computer or like the web version.
Yeah, that's a good point. I don't know if Hannah, you'll have to try that when you're remoting and see if that works. I don't know if that's going to cause any issues, but that is a good option. Yes.
When will this room be occupied by other classes?
Oh, that's a good question. I have no idea. When are there other classes in this room? Jocelyn, do you know? There aren't that many other classes in this room. What's there? Today, 1 to 4. Okay, what's that? What class is that, by the way? Instrument design. Oh, is it here? I didn't realize that. Oh, that stinks. So you got to work really quickly after class, right? Yeah. Although maybe if you're here and you're sitting in the back, I bet they'd probably let you stay if you're quiet, right? I know. How many people are in instrument design?
It's a small class.
It's a small class. So if you're working, I bet she'd let you stay. But make her kick you out, right? Make her do that awkward thing. Yeah. Oh, and Monday mornings is regression, and 9:30 to 12.
Yeah.
And I don't think Kylie's not in here for 6 Yeah. So I think those are the only ones. I think it's regression on Mondays from 9:30 to 12. Instrument design from 1 to whatever time they finish, and us. I think that's it for this semester. I don't think there are any other classes that are in here on a regular basis. Occasionally I know that they're like one-off. Sometimes like they'll bring the undergrads in here to have them do Excel or something, but that's very infrequent. So I wouldn't worry too much about that. Yeah.
Oh, no.
Oh, okay. Other questions? So we've got output. Let's look at it. Let's use this logic and go through it. Okay, so okay, so here, yeah. The output, yeah. The output file is automatically going to be saved in the same folder as the input file, and it's going to be given the same name. It's just going to have an extension .out. So the input file always has an extension .imp, and the output file have the same name with the extension .out, which, so you just have to be, actually, that can get confusing sometimes if you're not looking at the extension. It's like, which one's my input, which one's my output, but it will automatically be there.
And it also automatically creates another like DGM.
It also creates a DGM, which is like a diagram file. That's a diagram file. So actually, let's see. So we ran this. So if you go to diagram, so the DGM file, they're not very pretty, okay? But if you go to view diagram, there it is. It's like, so it's actually drawn out. You see what I mean? It's like, oh, okay. I just went to, hold on. I gotta get out of here. Okay, there we go. So you just go to diagram, click on view diagram, and then it'll come up. And then there are some options actually. So let's see, you can view, here we go. So right now it's showing me residuals as arrows, but I could change that if I wanted to see them as little variables. See how it just made the little residuals with the little latent variables. I also, right now it's showing me unstandardized parameter estimates, but maybe I want to see the standardized estimates, so I can click on that. I can also, let's see. Oops, view. Thank you. I might want to show only the estimates and not like the standard errors. So I can do that. Sometimes that's just easier to look at it first, right? I can show no estimates. So now I just see the paths, right? I can show only the significant things. Maybe I want to show that with the estimates. So there you go. So now you kind of, again, it's not as pretty because it's just kind of drawn it. Maybe it's not like logically. You can move stuff around, by the way. But there you go. So I could be like, yeah, I kind of want it to look like more like this. Let's see here. Oh, look, that looks a little better, right? It's a little easier to look at because it looks a little bit more like ours. Even so, I wouldn't say these are publication ready diagrams. I mean, I tend to, like when I'm publishing stuff, I don't use the diagrams from Mplus. But they are useful for, I mean, they can be useful for looking at. They're certainly useful for homework, you know. So those are the, okay. So now we saw, actually, because this says only the significant, well, I didn't really want to do that because I don't want to look at the conceptual paths yet. I only want to look at my, and it doesn't know which paths I want to look at yet. So let's go back to view. Let's get rid of the show only significant. Okay, there we go.
Is there a better program to draw a path diagram?
Sure, like any program is better. I mean,
Something specifically for SEM.
you know, I'm not very good at drawing diagrams. I mean, I will often use like Word. I'm sure there's a better package than that. Amos, yeah, I have used Amos. I gotta say that is one thing I like. I have done that. I have drawn stuff in Amos just to have the drawing, even though I estimated the whole thing in Mplus, because it's much those are much prettier. So like Amos or Word, or I mean, I'm sure there are other graphics packages that are nicer, you know, but so you can mess around and sort of, but yeah, I mean, I think Word works fine, actually, generally. Okay, so let's take a look at our output before we run out of time to look at our output. So looking at, this is the conceptual model. Let's look at model 1. I think I have model 1 here somewhere. Just identified, here we go. Okay, so look at the model 1, and you can see here, let's just look through the output together. So the summary of analysis is just telling me like a number of observations is how many people. So there are 619 observations in this data file. Number of groups. If you were running a multiple group model, you'd have more than one group, but here you just have one group. It tells you how many dependent and independent variables. So that's like exogenous and endogenous here, right? And then it tells you what it thinks. Like, oh, I think your endogenous variables that are, and it says continuous, like it's assuming these are continuous, are GPA, homework, and motivation, self-regulation. And those exogenous variables are academic self-perception and goal evaluation. Next, it tells you about sort of some stuff about the estimator. We'll come back to talking about estimation later. And then it gives you sample statistics, which again, here are literally, because we have no missing data, are literally our sample statistics. So it gives you the means on each of these variables, and then it gives you the covariances between those variables. And then it gives you the correlations. It gives you a correlation matrix, which can be really helpful to look at too. You know, and just as a sort of interesting, like look at GPA. Looks like, you know, goal evaluation and GPA are not very correlated at all. It's like 0.06 and 0.09, the correlation between homework and GPA. Interesting. Okay. So
Is it a real data? This
What?
one? Is it a real data?
yeah, these are real data. These are real data. They're old now, but they're real. Okay, so then we just get some, again, you want to do your screening and cleaning in another package, but it is a little bit helpful that you get this univariate sample statistics tells you about the means, the variances, skewness and kurtosis, what's the maximum and minimum. So you can see like the minimum on GPA. So this is like on a 0 to 10 scale actually, which is unusual, but so that makes sense though, it's 0 to 10. And then it sort of tells you what the median is, the 20th percentile and 60th percentile, 40th and 80th percentile. So you can kind of get a sense of the distributions of your variables from that. Then you want to see this line. This is like a magical line. The model estimation terminated normally. Yay! Hooray! It tells us how many free parameters there are in the model. So that's how many parameters we're estimating. Don't worry about that right now, though, actually. Worry more about the degrees of freedom, okay? And then it tells us what our chi-square is and our degrees of freedom. So you can see here we have a chi-square of 0 with 0 degrees of freedom, which makes sense because it was a just identified model. We haven't talked about model fit statistics yet, but of course they all look awesome because we have a just identified model. And then finally we get our model results. So we get our estimates, standard errors, we get the, that ratio of the estimate to the standard error, and then the two-tailed p-value for all of those. So let's start by looking at those 3 conceptually omitted paths. So let's remind ourselves what they are. So we didn't think we needed the path from motivation self-regulation to GPA. So that would be GPA on SR. And you can see that these are under model results, these are the unstandardized model results, okay? So the unstandardized path coefficient is 0.194. Oh, I should bring this up on the, right? Instead of looking at this diagram here for a second. Well, actually, I guess we could look at it there too, but let's pull up the output. Okay, so.
That's it, just a quick question.
Yes.
The number of base branches, is that on the number of nodes that is 20 here? Because the number of nodes.
Yeah, okay, so no, so yes, it is, but don't look at it.
Okay.
Because, and we'll come back to it later in the semester, because it's also counting the number of elements in the mean vector. So it's not going to necessarily, those number of nodes are not necessarily going to match the number of nodes that you have, because it's counting, it's actually counting means as well as variance covariance elements. So look at the degrees of freedom rather than the number of nodes for now. When we get later in the semester and we add in means, then we'll be good to look at that. But if you think, oh, that doesn't match, it doesn't. Okay, but just to expound on that for a minute, in all the models that we're going to be doing until the middle of the semester, the means are both knowns and unknowns. So it will never change our degrees of freedom. We will have as many means, we will estimate as many means and intercepts as we have mean pieces of information. So we'll up the number of known parameters here, but it will never change our degrees of freedom, and it will never change the number of unknowns. So yeah, that's why it's different. All right, where was I? Oh yeah, so you see goal valuation, GPA on goal valuation. No, whoops, that wasn't one of them. Sorry, I highlighted the wrong one. GPA on motivation self-regulation. That's one of our conceptually deleted paths. The path coefficient is 0.194. Standard error is 0.105. You can see it's not statistically significant at a 0.05 level. The p-value is 0.065. Okay, so, and again, power is not an issue here. We've got 619 people. So, okay, so it's not statistically significant, so I don't think I need that path. I didn't think I needed it, and it looks like I really don't need it. So, yay. Now, next, I think it was homework on motivation. No, not motivation. Homework on academic self-perceptions and homework on goal evaluation, right? Those were the other 2 deleted paths. So let's check those. So motivation on academic self-perception. Here we have the parameter estimate is negative 0.028. The p-value is 0.778. Yeah, not even close, right? Don't need that path. How about homework on goal evaluation? Parameter estimate's negative 0.171. The p-value is 0.144. I don't need that. I don't need that path either. Those are the only 3 that I'm looking at right now. Well, I'm not going to look at my conceptual paths yet. I'm going to rerun this model, deleting the paths that I didn't think I needed that I now know I can delete. So does everybody follow the logic there? Okay. So next, we are going to come back. Oh, there's really not anything else, that we need to look at here. So let's go to model 2, save changes. I don't know. I don't think I made any changes. Okay. So now the conceptually omitted paths, this is why I did it this way. I can just comment out. Okay, and I'm going to save this as in-class example. I'm going to call this 2 for right now, right? I don't want to save over my other input file. And again, you have to have separate input files for every model. That's like just kind of annoying, but it is what it is.
How
And
did you get to this input file from the output one?
I just closed my output file and it was right underneath there because I never closed out my input file. So I said, if you close your input, you can just always go back to file, open, and open your input file. Okay, so now I'm going to run this input file, right? And okay, all the sample statistics stuff should be the same. And now check this out. So first thing to notice is that I have 3 degrees of freedom. That makes sense because I just omitted the 3 conceptually omitted paths, right? So I just made 3 constraints. So I picked up 3 degrees of freedom. My chi-square is 5.794 with 3 degrees of freedom. And that chi-square is not statistically significantly different from 0. Which means, so the first thing is, that actually means it's a pretty good fitting model. So in terms of model fit, a non-statistically significant chi-square is good. That means we have a good fitting model. I mean, it means that our, there's reasonable, right? Model data convergence is good. And so the model fits well, but also if I wanted to do a chi-square difference test, well, it turns out because it was a just identified model, this is also the chi-square difference test, right? Because 5.794 minus 0 is 5.794, and 3 degrees of freedom minus 0 degrees of freedom is also 3 degrees of freedom, right? And so in this case, because we're comparing it to a just identified model, the chi-square difference test is actually the same as the chi-square test here. So this is telling me that I can make that set of 3 constraints. I already looked and saw that each one of them individually were non-statistically significant. But now this is saying, you know what, you can make those 3 constraints and the model fit did not get appreciably worse. The model fit is still, basically, this model fit is not statistically significantly worse than the just identified model, where the just identified model fit is not significantly better than the fit of this model, which again, from a parsimony perspective, means that we're going to favor this model, which is good news because this is the model I wanted all along, right? Yeah, questions. I see you. Oh, it's in my output for this. So it's right after the model estimation terminated normally, model fit information, and I just went down to the chi-square tested model fit. So that's good, right? So yay. So now what I would do is go and I would interpret my model parameters. It might be easier to look at the standardized estimates versus the unstandardized estimates. But now if I wanted to trim the model, this is where I would look at are all of my conceptual paths necessary. And you can see actually, okay, here are my conceptual paths right here. So most of them have p-values of less than 0.001, right? But there is one that actually stands out, which is goal valuation on GPA, which has an estimate of negative 0.17, and the two-tailed p-value is 0.077. So after controlling for academic self-perceptions and homework, there doesn't seem to be a statistically significant, right, direct effect from goal valuation to GPA. So if I wanted to trim this model, that would be the path that I would trim out. And then I would refit that model with that path trimmed out. And then I could do a chi-square. Actually, I can do that really quickly and look at the chi-square there. Oh, no, I can't. It's 12:15. But you get the idea. I could, right? You could do that on your own really quickly and look at the chi-square. And that's it. That's how you do this thing. So homework. We didn't.
Edit in person next week, and then upload your code onto Husky C2 without trying to hold.
Yeah, but we didn't get to CFA. So I think give me a few minutes, and I'm gonna swap out. Do I want to do that? Do I want to just have them do the first part of homework today? What do you think? We just do the first part. There's not much to be gained by doing it
We
the,
could do,
the opposite direction.
I was gonna suggest that.
We could do that. We could do that. What do you think? Should we go back to the original homework too?
And then just crop off our students. Or look at it.
Yeah. I'm gonna give you all a break. You just have to do the first part of homework 3. All right. And then next week we will talk about how to fit CFA models, and then you'll do the CFA part next week along with whatever else the homework was for next week. We'll figure that out. We'll combine some homework. So homework 3 right now, you just have to do the first half.
Is that gonna be clearly defined like in order go?
Well, not right now, it isn't, but, I mean, yeah, it's really obvious. There's a path model one and then there's a CFA one.
Okay.
So just do the path, I mean, if you want to do the CFA one, help yourself, but we haven't talked about it yet. So just do the path model one. That's all that we'll grade at for next week, is just the path model part, and then you'll get the CFA part along with something else for next week's homework. Does that make sense? All right. Cool. All right. Well, I see you all next week.
No, hey, I also brought their homework too, right?
Well, so you need to-
Everybody uploaded? Okay.
All right. So now, oh, I should stop the recording. Stop the recording. Let's see.
Thank you, Betsy.
Sure.